Welcome, we're so happy you tuned in tonight. Before we get started, I'd love to know, where are you watching from? Drop it in the comments. Now, let's get comfortable and drift into deep, peaceful sleep together. The universe is not empty. It might look that way on a clear night when you tilt your head back and see the darkness between stars, but that darkness is not a void. It is furnished. Between the points of light, drifting through the enormous distances that separate one star from another, there are tiny solid particles floating silently in space. These particles are called cosmic dust, and they are real physical material. Not a metaphor, not an abstraction, but actual grains of matter, each one smaller than you could see with your naked eye, scattered across the galaxy and beyond. Tonight we're going to walk through 100 small facts about cosmic dust, each one a gentle step into understanding the fine texture of the universe. You do not need to memorize them. You do not need to hold on to them. Just let them pass by like particles drifting through a sunbeam, and if sleep finds you along the way, that is exactly right. Cosmic dust exists across space. It is not confined to one special region or reserved for exotic locations. It floats between stars in our own galaxy, gathers in clouds where new stars will someday form, and drifts in the space between galaxies as well. When astronomers look out at the universe, they are always looking through some amount of dust, even if they cannot see it directly. The dust is there, mingling with the thin gas that fills interstellar space, creating what scientists call the interstellar medium. This medium is not truly empty. It is a mixture, mostly gas with a small fraction of solid dust grains mixed in. The gas is far more abundant by mass, but the dust plays a role that is larger than its small quantity might suggest. Even though dust makes up only about 1% of the mass of the interstellar medium, it has a profound effect on how we see the universe and how stars and planets come to be. Each grain of cosmic dust is extremely small. If you were to hold one in your hand, you would not be able to see it without a microscope. Most dust grains are less than a micrometer across, smaller than a red blood cell, closer in size to the particles in cigarette smoke or fine talcum powder than to grains of beach sand. Some are even smaller, just a few dozen nanometers wide, while others might reach a micrometer or slightly more. They are irregular in shape, not perfect spheres, and their surfaces are rough and varied. Despite being tiny, these grains have power. They can block light, they can scatter it, they can absorb energy from nearby stars and re-radiate it in different forms. A single grain does very little, but when trillions upon trillions of grains gather together in a cloud, they can hide entire regions of a galaxy from view, or glow softly in wavelengths of light that our eyes cannot detect. Cosmic dust is made of mixtures. There is no single recipe that applies everywhere, because dust grains form in different environments, and from different materials, some grains are rich in carbon. These carbonaceous grains might include graphite similar to the material in a pencil, or more complex carbon compounds. Other grains are made of silicates, minerals that contain silicon and oxygen, often combined with elements like magnesium, iron, or aluminum. These silicate grains are somewhat similar to the minerals found in rocky planets, including Earth. In the coldest parts of space, dust grains can also accumulate icy coatings, thin layers of frozen water, carbon monoxide, carbon dioxide, methane, or ammonia. These ices cling to the grain surface and can change the grain's properties, making it slightly larger and altering how it interacts with light and with other molecules in space. The composition of a dust grain tells a story about where it came from and what it has experienced. Dust is not the same everywhere. Its composition depends on local conditions. In regions where old, cool stars are gently releasing material into space, the dust might be rich in carbon or silicates, depending on the chemistry of the star's outer layers. In areas where massive stars have exploded in the past, the dust might contain heavier elements forged in those explosions. In dense clouds where molecules are forming and ice is accumulating, the grains might be coated and chemically different from grains drifting in the emptier regions between clouds. As dust travels through space, it can be altered by radiation from nearby stars, by shock waves from stellar winds or supernovae, or by collisions with other particles. Over time, a single grain might be processed and reprocessed many times, its surface etched or coated, its structure changed. The universe is not a factory with one assembly line. It is a vast and varied workshop where dust is constantly being made, modified and recycled. There can be long distances between individual dust grains, especially in the less dense parts of space. If you could shrink yourself down and float between the stars, you might drift for a very long time before encountering a grain. The space between grains is measured in meters, sometimes kilometers, depending on the local density. Yet despite these large gaps, when you consider the enormous volumes involved, cubic light years of space, the total amount of dust becomes significant. A region might contain only a few grains per cubic meter, but multiply that by the volume of an interstellar cloud, and you have trillions upon trillions of grains contributing to the cloud's overall properties. Dust does not need to be tightly packed to have an effect. It just needs to be present, spread out over vast distances, waiting patiently. In space, dust can drift for ages without being disturbed much at all. There is no wind in the conventional sense, no rain to wash it away, no surface for it to settle on. A dust grain can float along, carried by the faint pressure of starlight or the thin currents of gas flowing through the galaxy, travelling for thousands or millions of years without a significant collision. It is motion at a pace so slow and gentle that it makes a glacier look hurried. The grain is not in a rush, it has nowhere urgent to be, it simply exists, drifting, occasionally interacting with a photon of light or brushing against a gas molecule, but mostly just moving through the silence, a tiny solid island in an ocean of near vacuum. This stillness is part of what makes cosmic dust so calming to think about. It is matter in no hurry, shaping the universe over timescales that dwarf human lifetimes. The motion of dust grains is influenced by forces that are almost imperceptible on human scales, but significant over cosmic time. Radiation pressure, for instance, is the gentle push that light exerts when it strikes a dust grain. Each photon carries a tiny amount of momentum, and when it hits a grain, some of that momentum is transferred. For a single photon hitting a single grain, the effect is negligible. But a dust grain near a bright star is being hit by countless photons every second, and over time, this steady pressure can push the grain outward, away from the star. Small grains are pushed more easily than large ones, because the force depends on the grain's surface area, while resistance to movement depends on its mass. Very small grains can be blown out of star systems entirely by radiation pressure, while larger grains resist this force and remain closer to their parent stars. This sorting by size is one of the ways the universe organizes matter without any conscious intention, just physics acting patiently over time. Dust grains can also be influenced by magnetic fields. The interstellar medium is threaded with weak magnetic fields, invisible but real, extending across vast distances. Some dust grains contain magnetic materials like iron, and these grains can align themselves with the local magnetic field, much like a compass needle aligns with Earth's magnetic field. When grains align, they affect how light passing through the dusty region is polarized. By measuring this polarization, astronomers can map the magnetic fields in molecular clouds and other regions, revealing the invisible structure that shapes the movement and behavior of gas and dust. Magnetic fields can also influence how clouds collapse to form stars, providing support against gravity in some cases and channeling material in specific directions in others. Dust becomes a tool for studying these fields, a visible tracer of invisible forces. Just one more small fact, and then we drift. Sometimes, when astronomers look at images of space, they see dark patches that appear to be holes in the star field. These dark regions look empty, as if there are simply no stars there. But often that darkness is an illusion. The region is not empty. It is filled with dust. Dust clouds can block visible light very effectively, creating dark nebulae that stand out against the brighter background of more distant stars. The dust does not destroy the light, it absorbs it and scatters it. When visible light from a star encounters a dust grain, some of that light is absorbed by the grain, and some is scattered in different directions. If the dust cloud is thick enough, very little visible light makes it through to reach our eyes or our telescopes. The result is a shadow, a dark silhouette where a cloud of dust hangs between us and the stars beyond. These dark regions are not voids, they are veils. One of the most famous dark nebulae is the Coal Sack, visible in the southern hemisphere. It appears as a dark patch in the Milky Way, a region where the brightness of the galactic band is interrupted by what looks like a hole. But the Coal Sack is not a hole, it is a molecular cloud filled with gas and dust, located about 600 light-years from Earth. The The cloud blocks the light from the stars behind it, creating the illusion of emptiness. If you could travel to the coal sack and look around from inside it, you would see dust and gas, surrounding you, faintly illuminated by the light of distant stars. You would not perceive it as a void. The darkness is purely a matter of perspective, a consequence of standing on the far side and looking through a dusty curtain. Dust can absorb starlight and warm slightly. When a dust grain absorbs a photon of visible or ultraviolet light, that energy is converted into heat. The grain's temperature rises by a tiny amount. Because the grain is solid, it can then re-emit that energy, but not in the same form it received it. Instead of giving off visible light like a hot star would, the dust grain radiates energy at much longer wavelengths, in the infrared part of the spectrum. This re-emission is gentle and quiet. Infrared light is lower in energy than visible light, more like warmth than glare. The grain glows softly in the infrared, invisible to our eyes but detectable by instruments designed to see heat. This process transforms the light of the universe. A bright star might pour out visible and ultraviolet light. But if that light passes through a dusty region, some of it is converted into infrared glow, changing the energy budget of the surrounding space. The temperature of a dust grain depends on its distance from nearby stars and on the intensity of the radiation it receives. Close to a hot, bright star, dust grains can be warmed to several hundred degrees Kelvin, warm enough to glow brightly in the mid-infrared. Farther away, in the cold outer regions of a molecular cloud, dust grains might be only a few tens of degrees above absolute zero, emitting faintly in the far infrared and sub-millimeter wavelengths. The grain does not hold on to heat indefinitely. It radiates energy continuously, finding a balance between the energy it absorbs and the energy it emits. This balance is dynamic and depends on the local environment, making dust a sensitive indicator of conditions in different regions of space. This means that darkness in visible light can hide brightness in infrared. A cloud that looks completely black in an optical photograph might light up beautifully when observed with an infrared telescope. The dust is quietly glowing, warmed by the hidden stars embedded within the cloud or by nearby stars whose light has been absorbed. Astronomers have learned to look at space in multiple wavelengths precisely because dust changes what is visible. A region that seems cold and empty in one kind of light can reveal itself as warm and active in another. The universe has layers of visibility, and dust is one of the things that creates those layers. It is a reminder that seeing is not always straightforward, that what looks dark might only be dark in one narrow slice of the electromagnetic spectrum. Infrared observations have transformed our understanding of star formation. Before infrared telescopes became widely available, astronomers could only study the later stages of starbirth when young stars had cleared away enough of their surrounding dust to be visible in optical light. But the earlier stages, the collapse of a cloud core, the formation of a protostar, the assembly of a protoplanetary disk, all happen hidden inside thick dust envelopes. Infrared light can penetrate these envelopes, allowing astronomers to see what is happening inside. They can watch as material falls onto a growing protostar, observe the structure of the disk where planets will form, and measure the temperature and density of the surrounding gas and dust. Infrared astronomy has opened a window onto processes that were previously invisible, revealing the messy, complex reality of how stars and planets come into being. Dust also filters light by scattering. When starlight passes through a dusty region, blue light is scattered more efficiently than red light. This happens because blue light has a shorter wavelength, and dust grains of certain sizes are particularly good at redirecting short wavelength light in random directions. Red light with its longer wavelength is less affected and passes through more easily. The result is that the starlight emerging from the other side of a dust cloud is redder than it was when it went in. Astronomers call this process interstellar reddening or extinction, though the light is not truly extinct, just filtered and redistributed. The effect is similar to what happens during a sunset on Earth, when the sun's light passes through a long path of atmosphere and dust, scattering away the blue and leaving the reds and oranges to reach our eyes. In space, this reddening is permanent for any observer looking through the dust, giving distant stars a tinted appearance like a cosmic sunset that never ends. The amount of reddening depends on the amount of dust along the line of sight and on the properties of the dust grains themselves. Larger grains scatter light differently than smaller grains, and grains with different compositions have different scattering properties. By carefully, Measuring the colours of stars and comparing them to what those colours should be based on the star's temperatures and spectral types, astronomers can determine how much reddening has occurred. This, in turn, tells them how much dust lies between Earth and the star. It is a technique that requires precision and care, but it provides valuable information about the distribution of dust in the galaxy and helps correct observations for the effects of extinction. This scattering effect has practical consequences for astronomers. When they measure the brightness and colour of a distant star, they have to account for the dust between here and there. If they do not, they might think the star is cooler and dimmer than it really is, because the dust has made it look redder and has blocked some of its light. By studying the amount of reddening, astronomers can estimate how much dust lies along the line of sight and correct their measurements accordingly. Dust becomes a factor in almost every observation of distant objects. It is a kind of tax that space imposes on light, a subtle alteration that must be accounted for if you want to understand what you are truly seeing. Interstellar extinction varies with wavelength in a predictable way, and astronomers have developed mathematical models called extinction curves to describe this variation. These curves show how much light is absorbed and scattered at different wavelengths, from the ultraviolet through the visible and into the infrared. The shape of the extinction curve depends on the size distribution and composition of the dust grains, and by fitting observed extinction to these models, astronomers can learn about the properties of the dust. For example, a feature in the ultraviolet part of the extinction curve, known as the 20 angstrom bump, is thought to be caused by small carbon-rich grains. The presence and strength of this feature tells astronomers about the abundance and nature of carbonaceous dust in different regions. Dust is one reason the universe can look different depending on the kind of light you use to observe it. In visible wavelengths, dust creates dark lanes and obscures whole sections of galaxies. In infrared, those same regions glow warmly, revealing star formation and hidden stellar populations. In ultraviolet, dust blocks light even more strongly, making regions with heavy dust appear almost completely dark. In radio wavelengths, dust has less effect, and you can often see through it to structures and emissions that are invisible in optical light. Each wavelength is a different window, and dust controls how transparent each window is. Astronomers have to choose their windows carefully, depending on what they want to study, and they often combine observations from multiple wavelengths to build a complete picture. Dust is both an obstacle and an informant. It hides some things, but in hiding them, it also tells us where the hidden things are. The development of the multi-wavelength astronomy has been one of the great advances of modern astrophysics. By observing the same object or region in many different wavelengths, gamma rays, X-rays, ultraviolet, visible, infrared, submillimeter, and radio, astronomers can piece together a comprehensive understanding of what is happening. Each wavelength reveals different physical processes and different components of the system. Dust is often the key to interpreting the differences between wavelengths, because its presence so strongly affects what can be seen. A complete picture of a star-forming region, for example, might include visible images showing the young stars that have emerged, infrared images revealing protostars still embedded in their birth clouds, radio observations mapping the molecular gas, and submillimeter data tracing the coldest dust. Together, these observations tell a story that no single wavelength could tell alone. Just one more small fact and then we drift. The space between stars in a galaxy is called the interstellar medium. It is a mixture of gas and dust, spread out over the vast distances that separate one star from another. The gas is mostly hydrogen, the simplest and most abundant element in the universe, with some helium and trace amounts of heavier elements. The dust is the solid component, the tiny grains we have been describing drifting along with the gas. The interstellar medium is thin, far thinner than any vacuum we can create on Earth, but it is not nothing. It is the fabric from which new stars are made. In certain regions, the interstellar medium becomes denser, gathering into clouds where gravity can begin to pull material together. These clouds are the nurseries of stars, and dust is a crucial part of the process. The interstellar medium is not uniform. It has structure, with regions of different densities, temperatures and compositions. Some regions are diffuse and warm, with gas spread out thinly and dust grains separated by large distances. These regions might have densities of only a few atoms per cubic centimetre and temperatures of thousands of degrees. Other regions are cold and dense, with densities reaching millions or even billions of atoms per cubic centimetre, and temperatures just a few degrees above absolute zero. These cold, dense regions are molecular clouds, where gas atoms have come together to form molecules and where dust is abundant. The interstellar medium is constantly changing, stirred by stellar winds, supernova explosions, and the gravity of passing objects. It is a dynamic environment, full of motion and transformation. Dust often gathers in the spiral arms of galaxies. Spiral galaxies, like the Milky Way, have beautiful curved structures that sweep outward from the galactic centre. These spiral arms are not solid structures, they are density waves, regions where stars, gas and dust crowd together more closely than in the spaces between the arms. As gas and dust move through a spiral arm, they are compressed, and this compression can trigger the formation of new stars. Because dust is part of the interstellar medium, it tends to be more concentrated in these arms as well. The spiral arms are where star formation is most active and where dust plays its role most visibly. The spiral structure of galaxies is maintained by gravitational interactions and orbital mechanics. Stars and gas orbit the galactic centre, but not all at the same speed. The differential rotation creates regions where material piles up temporarily, forming the spiral arms. These arms rotate more slowly than the stars themselves, so individual stars and clouds pass through the arms over time. When gas and dust enter a spiral arm, they experience increased density and gravitational forces, which can trigger collapse and star formation. The newly formed stars light up the arm, making it visible and prominent. As these stars age and the gas and dust move on, the arm persists as a wave pattern, continuously fed by new material entering from behind. Dust lanes in spiral galaxies are beautiful dark streaks that trace where dust is thicker. When you look at an edge-on spiral galaxy, you can often see a dark band running along the plane of the galaxy's disk. This band is not empty space, it is dust, concentrated in the thin disk where the galaxy's gas and stars also reside. The dust creates a silhouette, a charcoal-like line that shapes the galaxy's appearance. These dust lanes are a signature feature of spiral galaxies, and they tell astronomers where the raw material for future stars is located. Even in face-on spirals, you can see darker patches and streaks winding along the spiral arms, outlining the structure in shadow. The dust lane in an edge-on galaxy can be remarkably thin compared to the galaxy's overall size. A typical spiral galaxy might be tens of thousands of light-years across, but the dust layer might be only a few hundred light-years thick. This thin layer marks the mid-plane of the galactic disk, where gravity has pulled the dust and gas into a concentrated sheet. The thinness of the dust layer is maintained by a balance between gravity, which pulls material toward the midplane, and the random motions of gas clouds which cause the layer to puff up slightly. The result is a delicate structure, a flat ribbon of dust threading through the galaxy, visible as a dark line when seen from the side. Our own galaxy, the Milky Way, is a spiral galaxy, and we live inside its dusty disk. When we look up at the night sky, the Milky Way appears as a band of light arcing across the heavens. This band is our view of the galaxy's disk from the inside, looking through the plane where most of the stars, gas and dust reside. In some directions the band looks dense and bright, crowded with stars. In other directions there are dark patches and gaps, regions where dust blocks our view of more distant stars. Dust within the galactic plane is one reason the night sky looks richer and more textured in some directions than others. It is also why we cannot see all the way across the galaxy in visible light. There is simply too much dust in the way, absorbing and scattering the light before it reaches us. Our position in the Milky Way's disk gives us a unique but limited perspective. We are located about 26,000 light-years from the galactic centre, in a region known as the Orion Arm, or Orion Spur, a minor spiral arm between two major arms. From this position, looking inward toward the centre of the galaxy, we look through a long path of dust and gas in the galactic plane. Looking outward, away from the centre, we look through less dust, and our view is clearer. This is why the part of the Milky Way visible in the direction of the constellation Sagittarius, toward the galactic centre, appears so dense and dramatic, while the part visible in the opposite direction, toward Auriga and Perseus, is less intense. Dust shapes our view and determines what we can see from our particular vantage point. The galactic centre is an example of a region that is bright in many wavelengths, but difficult to see in visible light from our position. The centre of the Milky Way is located about 26,000 light-years away, in the direction of the constellation Sagittarius. It is a crowded, energetic place, home to millions of stars, clouds of gas and dust, and a supermassive black hole with a mass of about 4 million times that of the Sun. But when we try to observe it in visible light, we see very little. The dust along the line of sight absorbs and scatters most of the visible light before it can reach Earth. To study the galactic centre, astronomers use infrared and radio telescopes, which can see through the dust. In those wavelengths, the centre reveals itself, a bustling hub of activity hidden behind a dusty curtain. The dust does not make the galactic centre disappear, it just makes it invisible in certain kinds of light, reminding us that what we see depends on how we choose to look. Infrared observations of the galactic centre have revealed a complex and dynamic environment. There are dense clusters of stars, some of them orbiting very close to the central black hole. There are massive clouds of gas and dust, some actively forming stars and others being disrupted by intense radiation and winds from nearby massive stars. There are filaments of hot gas, loops of magnetic field, and structures shaped by past explosions and outflows. The galactic centre is not a calm place. It is one of the most energetic and chaotic regions in the Milky Way. But from our perspective, hidden behind dust, it appears almost invisible in visible light. Dust has preserved its secrets for most of human history, only revealing them when we developed the technology to observe in other wavelengths. Just one more small fact, and then we drift. Star-forming regions are places where the interstellar medium has gathered into cold, dense clouds. These molecular clouds are thick with gas and dust, and they are some of the coldest environments in the galaxy, with temperatures often just a few tens of degrees above absolute zero. In these frigid conditions, gravity can begin to pull material together. Over time, clumps within the cloud grow denser, and as they do, they begin to heat up. Eventually, if a clump becomes dense and hot enough at its core, nuclear fusion ignites, and a new star is born. But this process does not happen quickly or easily. It takes time, and it requires help. Dust plays a helpful role in this slow transformation. The journey from cloud to star can take millions of years. It begins with a molecular cloud, a vast region of space filled with gas and dust, often extending for tens or hundreds of light years. Within this cloud, there are variations in density. Some regions are slightly denser than others, perhaps because of turbulence in the gas, or because a passing shock wave from a supernova or stellar wind has compressed the material. These denser regions experience slightly stronger gravity, and they begin to pull in more material from their surroundings. As they grow, their gravity increases, and they pull in material even faster. This is the beginning of gravitational collapse, the process by which a cloud core becomes a protostar. Dust provides surfaces where molecules can form. In the cold environment of a molecular cloud, atoms and simple molecules drift around, occasionally colliding with the dust grain. When they land on the grain's surface, they can stick for a while, held by weak forces. While they are stuck, they have time to meet other atoms and molecules that have also landed on the grain. Chemical reactions that would be too slow or unlikely to happen in free space can occur on the grain's surface, where reactants are brought together and held in place. One of the most important reactions is the formation of molecular hydrogen, H2, from individual hydrogen atoms. Molecular hydrogen is the dominant molecule in star-forming clouds, and dust grains act as tiny laboratories where much of this molecule is assembled. Without dust, the chemistry of the interstellar medium would be different, and the process of star formation might be less efficient. The surface of a dust grain is not smooth or uniform. It has defects, irregularities, and active sites where atoms can bind more easily. When a hydrogen atom lands on the grain, it can wander across the surface, hopping from site to site until it encounters another hydrogen atom. When two hydrogen atoms meet, they can bond together to form H2, releasing a small amount of energy in the process. The newly formed molecule then evaporates from the grain's surface and drifts away into the surrounding gas. This process is happening continuously on countless dust grains throughout a molecular cloud, gradually converting atomic hydrogen into molecular hydrogen and building up the molecular content of the cloud. Dust also blocks light, and that blocking is helpful in star-forming clouds. When a cloud is dense and cold, It needs to stay cold in order to collapse under its own gravity. If too much energy enters the cloud from nearby stars, it can heat the gas and create pressure that resists collapse. Dust grains absorb that incoming light, preventing it from heating the gas as much as it otherwise would. The dust then re-radiates the energy as infrared light, which can escape from the cloud more easily. In this way, dust acts as a cooling agent, helping the cloud shed excess energy and maintain the cold, dense conditions needed for gravity to do its work. It is a gentle thermostat, regulating the temperature by transforming high-energy visible and ultraviolet light into low-energy infrared. This cooling process is essential for star formation. Without it, the thermal pressure in the cloud would be too high, and gravity would not be able to overcome it. The cloud would remain stable, neither collapsing nor dispersing, and stars would never form. Dust allows the cloud to cool below the temperature at which thermal pressure balances gravity, tipping the balance in favour of collapse. Once collapse begins, the process accelerates. As the cloud core contracts, it becomes denser and gravity becomes stronger. Material falls inward, heating up as it converts gravitational potential energy into kinetic energy. At the centre of the collapsing core, a protostar begins to form, growing as it accretes material from the surrounding cloud. Once a cloud begins to collapse, dust grains begin a new role. They start to collide and stick together. In the densest parts of a collapsing cloud, where a new star is forming, there is often a disk of material orbiting around the young star. This disk is made of gas and dust, and it is the leftover material from the collapse. Within the disk, dust grains move around, occasionally bumping into each other. When they collide, gently they can stick together, held by weak forces like static electricity or van der Waals forces. Each collision that results in sticking makes the grain a little bit larger. Over time, two grains become one slightly bigger grain. That bigger grain can collide with others and grow larger still. This process is slow and delicate. If the collisions are too violent, the grains shatter instead of sticking, but in the right conditions, it works. The sticking process depends on the properties of the grains and on the conditions in the disk. Grains with icy coatings tend to stick together more easily than bare grains, because the ice can act like glue, binding the grains when they touch. Temperature plays a role too. If the disk is too warm, the ice evaporates, and sticking becomes harder. Turbulence in the disk can cause collisions to be too violent, breaking grains apart instead of allowing them to grow. But in the cooler, calmer regions of the disk, the conditions are just right. Grains collide gently, stick, and grow, beginning the long process of building larger bodies. As dust grains stick and grow, they move from the realm of microscopic particles into the realm of pebbles. A pebble in the context of planet formation is not necessarily something you could hold in your hand. It might be anywhere from a millimetre to a centimetre or more in size, but it is much larger than the original dust grains. These pebbles are the intermediate stage between dust and planets. They continue to collide and grow, sometimes through gentle sticking, sometimes through gravitational attraction, as they become large enough to pull on each other. Over millions of years, these pebbles can accumulate into larger bodies called planetesimals, which are kilometres across and can have enough gravity to pull in more material actively. Planetesimals collide and merge, forming protoplanets, and eventually, if the conditions are right, a rocky planet like Earth or a core for a giant planet can form. The growth from pebbles to planetesimals is one of the most challenging aspects of planet formation to understand. There is a size range, roughly from centimetres to metres, where objects tend to be fragile and prone to breaking apart when they collide rather than sticking together. This has been called the meter-sized barrier, and it presents a puzzle for planetary scientists. How do growing bodies cross this barrier without being destroyed? Several mechanisms have been proposed. One idea is that turbulence in the disk can concentrate pebbles into dense clumps, where their combined gravity is strong enough to hold them together and allow them to collapse into larger objects. Another idea is that some bodies grow more quickly than others, perhaps because they start in a particularly dense region of the disk, and once they reach a certain size, they can accrete material gravitationally without needing to rely on collisional sticking. The details are still being worked out, but the general picture is clear. Somehow, the disk manages to build planetesimals, bridging the gap between tiny grains and kilometre-sized bodies. The peaceful big picture is simple. Worlds begin as dust learning to hold hands. Every rocky planet, every asteroid, every moon orbiting a gas giant started as tiny grains of dust in a disk around a young star. The details of planet formation are complex, with many processes happening at once: gravitational instabilities, collisions, migration, and interactions with gas. But the fundamental starting point is always the same: dust. Without dust, there would be no solid surfaces to stand on, no cores for planets to build around, no raw material from which rocky worlds could grow. Dust is not just background material. It is the seed from which solid worlds emerge. Protoplanetary disks are beautiful and varied. Observations with powerful telescopes, particularly in the infrared and submillimeter wavelengths where dust emits strongly, have revealed disks around young stars with rings, gaps, spirals, and asymmetries. These features are signatures of planet formation in progress. A gap in a disk, for example, might be carved out by a young planet whose gravity clears a path through the surrounding material. A spiral pattern might be caused by gravitational interactions between the disk and a massive planet, or by instabilities in the disk itself. By studying these structures, astronomers can learn about where planets are forming, how massive they are, and how they interact with the disk. Dust makes these observations possible because it is the dust that emits the infrared and submillimeter light that reveals the disk's structure. Many of the solid materials in rocky planets come from dust that existed long before those planets formed. The elements that make up Earth, the iron in its core, the silicon and oxygen in its rocks, the carbon in living organisms, were not created when Earth formed. They were forged in stars that lived and died billions of years ago. When those stars ended their lives, they released material into space, material that condensed into dust grains and drifted through the galaxy. That dust eventually found its way into a cloud of gas that would collapse to form the Sun and its planets. The dust became part of the disk around the young Sun, and from that disk Earth and the other planets grew. In a very real sense, the ground beneath our feet was once cosmic dust, floating silently between the stars. This connection between stars, dust, and planets is profound. It means that the atoms in our bodies have travelled through space, been part of stars, been expelled into the interstellar medium, condensed into dust, drifted for millions of years, and finally settled into the planets and life forms we see today. We are made of recycled material, stardust, in the most literal sense. This is not a poetic metaphor. It is the result of astrophysical processes that have been operating for billions of years. Every breath you take contains atoms that were once inside a star. Every rock, every drop of water, every living cell carries a history that stretches back to the earliest generations of stars in the universe. Just one more small fact, and then we drift. Dust is a traveller with many quiet origins. Not all dust comes from the same source, and not all dust is the same age. Some dust is freshly made, condensed from material released by stars in the relatively recent past. Other dust is ancient, having drifted through space for billions of years, surviving multiple cycles of cloud formation and starbirth. Understanding where dust comes from requires looking at the life cycles of stars, because stars are the primary factories where the elements that make up dust are created. Stars spend most of their lives fusing hydrogen into helium in their cores. This is a stable phase that can last for millions to billions of years depending on the star's mass. But eventually the hydrogen in the core runs out, and the star must find new sources of fuel. What happens next depends on the star's mass. Low-mass stars like the Sun swell into red giants, expanding and cooling as they begin fusing helium in their cores and hydrogen in a shell around the core. Higher mass stars go through more stages of fusion, creating heavier elements like carbon, oxygen, neon, and silicon. The details are complex, but the key point is that stars create new elements through nuclear fusion, elements that did not exist in the universe when it first formed. Older stars can shed material into space through gentle outflows. When a star like the Sun nears the end of its life, it swells into a red giant, its outer layers expanding and cooling. These cool, extended atmospheres are places where atoms can come together to form molecules and dust grains. The star's outer layers are not tightly bound. Stellar winds, driven by radiation pressure and pulsations, can carry this material away into space. As the material moves outward and cools, conditions become right for dust to condense. Carbon-rich stars produce carbonaceous dust, while oxygen-rich stars produce silicate grains. These grains, newly formed in the stellar wind, drift away from the dying star and enter the interstellar medium, joining the reservoir of dust that already exists. This process is gentle and gradual, a quiet contribution to the galaxy's dust budget. The amount of dust produced by a single star is small, but there are billions of stars in a galaxy, and many of them will go through this phase. Over millions of years, the cumulative contribution from all these stars is significant. Asymptotic giant branch stars, a specific phase in the evolution of low to intermediate mass stars, are particularly prolific dust producers. They pulsate, creating shocks in their outer atmospheres that help drive material outward, and they have strong stellar winds that carry the dust and gas away from the star. These stars are responsible for much of the dust production in galaxies today. Some dust is also made in more energetic cosmic events, though we can talk about these events calmly. When a massive star reaches the end of its life, it can explode in a supernova, a sudden and powerful release of energy. The explosion ejects the star's outer layers into space at high speeds, and within those ejected layers, elements heavier than hydrogen and helium are scattered. Carbon, oxygen, silicon, iron, and many others. As this material expands and cools, some of it condenses into dust grains. Supernova dust is rich in heavy elements, elements that were created in the star's core through nuclear fusion and during the explosion itself. This dust is dispersed into the interstellar medium, where it mixes with dust from other sources and becomes part of future generations of star-forming clouds. Supernovae are powerful, but the dust they create is part of a long, slow cycle, not an immediate catastrophe. Supernova dust was particularly important in the early universe, when galaxies were young and there were not yet many low-mass stars contributing dust through stellar winds. Massive stars evolve quickly, exploding as supernovae within a few million years of their formation, and they can produce substantial amounts of dust in a single event. This dust helped seed the early galaxies, providing the raw material for the first generations of planet formation and contributing to the opacity that shaped how those galaxies evolved. Observations of distant young galaxies have revealed large amounts of dust, more than can easily be explained by stellar winds alone, suggesting that supernovae played a major role in dust production in the early universe. Dust participates in long cycles, forming, drifting, getting processed by radiation and shocks, joining clouds, and eventually becoming part of new stars and planets again. A dust grain that forms in the wind of a dying star might drift through the galaxy for millions of years before it encounters a molecular cloud. In that cloud, it might be incorporated into a new star-forming region, where it helps cool the gas and provides a surface for chemistry. If it ends up in a disk around a young star, it might stick to other grains and become part of a growing planet. Or it might be destroyed, heated by radiation, shattered by a shock wave from a nearby supernova, or vaporized as it falls into a star. Even when destroyed, the atoms that made up the grain are not lost. They remain in space, available to form new dust later. This recycling is continuous and patient. Nothing is wasted. It just changes shape and location, over and over across billions of years. The timescale of this recycling varies. In the densest parts of the galactic disk, where star formation is active and the interstellar medium is constantly being stirred by stellar winds and supernovae, a dust grain might be cycled through clouds and stars relatively quickly, perhaps on timescales of tens to hundreds of millions of years. In the outer parts of the galaxy, where the density is lower and star formation is less frequent, a grain might drift for billions of years without being incorporated into a new star. Some grains are lucky. They avoid destruction and remain intact for most of the galaxy's history. Others are processed repeatedly, each cycle altering their structure and composition. The idea of recycling is comforting. It means that the universe is not running down in a simple linear way. It is renewing itself constantly. The dust that helps form stars today will someday be part of new dust, and that new dust will help form stars and planets in the future. The cycle connects the past and the future, linking the death of old stars to the birth of new ones. It also connects us to the rest of the cosmos, the atoms in our bodies, the elements in the air we breathe, the materials in the buildings and tools around us. All of these came from dust, and before that, from stars. We are made of recycled stardust, participants in a process that has been going on for billions of years and will continue long after we are gone. Dust also carries information. By studying the composition of dust grains, astronomers can learn about the conditions in which they formed. Grains rich in certain elements suggest they came from specific types of stars. Grains with icy coatings tell us about the cold environments they passed through. Isotopic ratios within grains can reveal details about nuclear processes in stars and supernovae. Some meteorites contain tiny grains that are older than the solar system, pre-solar grains that formed in other stars before our sun existed. These grains are messengers from the distant past, carrying information about the galaxy as it was billions of years ago. By analysing them in the laboratory, scientists can learn about the history of stellar evolution, nucleosynthesis, and the interstellar medium in ways that would be impossible otherwise. Dust is not just material, it is a record, a library written in atoms and minerals. Presolar grains are remarkable. They survived the collapse of the solar nebula and the formation of the solar system, somehow avoiding being vaporized or altered. They were incorporated into meteorites, which drifted through space for billions of years before falling to Earth, where scientists found them and recognized them as something extraordinary. By measuring the isotopic composition of these grains, researchers can determine which type of star they came from and when that star lived. Some grains show isotopic patterns consistent with red giant stars, others with supernovae, and still others with more exotic sources. Each grain is a tiny time capsule, a fragment of a star that existed long before the sun, preserved through billions of years of cosmic history. Just one more small fact and then we drift. Because dust blocks visible light, astronomers often use infrared and radio observations to see through dusty regions. Infrared light has longer wavelengths than visible light, and it is less affected by dust. While visible light might be almost completely absorbed and scattered by a thick dust cloud, infrared light can pass through much more easily. This makes infrared telescopes invaluable for studying star-forming regions, the centers of galaxies, and other areas where dust is abundant. Infrared astronomy is like feeling warmth instead of looking at brightness. It is a quieter kind of seeing, more subtle, but in many cases more informative. The development of infrared astronomy required overcoming significant technical challenges. Earth's atmosphere absorbs much of the infrared light from space, so ground-based infrared telescopes have to be located at high, dry sites where the atmosphere is thinner and contains less water vapor. Even then, many important infrared wavelengths can only be observed from space. Infrared detectors also have to be cooled to very low temperatures to reduce thermal noise, which can overwhelm the faint signals from distant objects. Despite these challenges, infrared astronomy has flourished, with missions like the Infrared Astronomical Satellite, the Spitzer Space Telescope, the Herschel Space Observatory, and the James Webb Space Telescope revealing the universe in unprecedented detail. Infrared telescopes have revealed whole populations of stars that were invisible in optical surveys. Young stars buried deep in molecular clouds, for example, can be detected by their infrared glow even when no visible light escapes. Protostars, still in the process of forming, are often surrounded by thick envelopes of dust that absorb all their visible light and re-emit it in the infrared. By observing in the infrared, astronomers can watch stars being born, tracking their growth and evolution in ways that would be impossible if they relied only on visible light. Infrared astronomy has also revealed the structure of dusty disks around stars, showing where planets might be forming and how material is distributed within those disks. It is a powerful tool for studying processes that are hidden by dust. Infrared observations have also transformed our understanding of galaxies. Many galaxies, particularly those undergoing intense star formation, emit most of their energy in the infrared rather than in visible light. This happens because the young, massive stars in these galaxies produce copious amounts of ultraviolet light, which is absorbed by surrounding dust and re-emitted in the infrared. In visible light, these galaxies might appear modest or even faint, but in the infrared they blaze brightly. Infrared surveys have discovered populations of these infrared galaxies, revealing a component of cosmic star formation that was previously hidden. Radio observations are another way to see through dust. Radio waves have even longer wavelengths than infrared, and they are affected by dust even less. Radio telescopes can detect emissions from molecules in dense clouds, trace the motions of gas, and map the magnetic fields that thread through dusty regions. Radio astronomy is particularly useful for studying the coldest and densest parts of molecular clouds, where even infrared light might struggle to penetrate. By combining radio and infrared observations, along with data from other wavelengths, astronomers can build a complete picture of what is happening inside dusty regions, how the gas and dust are distributed, how they are moving, and how they are interacting with each other and with nearby stars. Radio telescopes can also observe the emission from specific molecules, providing detailed information about the chemistry and physical conditions in molecular clouds. Molecules like carbon monoxide emit radio waves at characteristic frequencies, and by measuring the intensity and Doppler shift of these emissions, astronomers can map the distribution and velocity of the gas. This reveals the internal structure of clouds, showing where dense cores are located, how the gas is flowing, and whether there are outflows or jets associated with young stars. Radio observations complement infrared data, providing a different perspective on the same regions and adding to our understanding of the processes at work. Dust also creates some of the most beautiful and informative patterns in astronomy. In images of nebulae and galaxies, dust often appears as dark lanes or bright filaments, depending on whether it is blocking light or glowing with absorbed energy. These patterns outline clouds, trace spiral arms, and mark where future stars may form. Dust is an artist, shaping the visual appearance of the universe in ways that make abstract physics tangible and aesthetically moving. When you look at a photograph of a star-forming region, with its dark cores and glowing edges, you are seeing dust at work, blocking, scattering, absorbing and re-radiating light, all in the service of creating new stars. Some of the most iconic astronomical images feature dust prominently. The Horsehead Nebula, for example, is a dark cloud of dust silhouetted against a bright background nebula. Its shape, resembling the head of a horse, is sculpted by the distribution of dust and gas, carved by the radiation and winds from nearby stars. The pillars of creation in the Eagle Nebula are towering columns of gas and dust, their shapes defined by the erosion caused by intense ultraviolet light from young stars. These pillars are regions where new stars are forming, protected from the surrounding radiation by the dense dust and gas. Dust gives these structures their form, their visibility, and their scientific interest. Dust traces the skeletal structure of the interstellar medium. In maps of galaxies, dust follows the spiral arms, highlighting the regions where the interstellar medium is densest and most active. In maps of molecular clouds, dust shows where the cloud is thickest and where collapse might be beginning. Dust is not just an obstacle to observation, it is an indicator, a signpost that tells astronomers where to look for interesting phenomena. By studying where dust is and how it is distributed, scientists can learn about the large-scale structure of galaxies, the life cycle of the interstellar medium, and the conditions that lead to star formation. Dust is both subject and tool. It is the thing being studied and the means by which other things are studied. Infrared and radio observations have also taught us that dust is dynamic. It is not static scenery. It moves, changes, and responds to its environment. Dust can be pushed by radiation pressure from bright stars, creating bubbles and cavities in the surrounding medium. It can be swept up by stellar winds or supernova shockwaves, compressed into dense filaments where new star formation might be triggered. It can evaporate when exposed to intense ultraviolet light, releasing the atoms and molecules locked in its structure back into the gas. Dust participates actively in the physics of the interstellar medium, shaping and being shaped by the energetic processes happening around it. The interaction between dust and radiation is particularly important in regions near hot, massive stars. These stars emit intense ultraviolet radiation, which can heat and ionize the surrounding gas, creating what is known as an HI region. At the boundary between the ionized gas and the surrounding neutral material, dust is subjected to intense radiation. The dust absorbs the ultraviolet light and heats up, sometimes reaching temperatures of several hundred degrees. This hot dust glows brightly in the infrared, creating a bright rim around the HI region. The radiation pressure can also push the dust outward, creating a shell or bubble that expands into the surrounding medium. Over time, this can clear out a cavity around the star, redistributing the dust and altering the structure of the interstellar medium. Even in a quiet room, far from any telescope or cloud of interstellar gas, you're part of a universe where tiny grains drift, settle, and slowly build complexity over immense time. The same processes that create dust between the stars also created the materials in the world around you. The wood in furniture, the metal in electronics, the silicon in glass. All of these came from elements forged in stars, condensed into dust, and eventually incorporated into the Earth when the solar system formed. Dust connects the grand scale of galaxies to the intimate scale of daily life. It is a reminder that the universe is not something distant and separate. It is the foundation of everything we know, including ourselves. The story of dust is also the story of patience. Nothing in the universe happens quickly by human standards. Dust grains take thousands or millions of years to drift from one place to another. Stars take millions of years to form. Planets take tens of millions of years to grow. The recycling of material through stars, dust, and the interstellar medium takes billions of years. Yet all of these slow processes add up to create the rich and complex universe we see today. Dust teaches us that transformation does not require haste. It requires time, gentle forces, and the accumulation of countless small changes. Cosmic dust can dim starlight, but it also makes new light possible later, by helping shape the places where stars and planets are born. This duality is important. Dust is often thought of as an obstacle, something that gets in the way and makes observations harder. But it is also an enabler. Without dust, molecular clouds would have a harder time cooling and collapsing. Without dust, molecules like H2 might not form efficiently. Without dust, planets might not be able to grow from tiny grains into worlds large enough to hold atmospheres and oceans. Dust is both the veil and the seed, both the shadow and the foundation. It takes light away in one form and gives it back in another. It hides the present and makes the future possible. This is the 100th fact, but it is not the end of the story. The universe has been building with dust for billions of years, and it will continue long after this moment. Stars will keep forming, planets will keep growing, and dust will keep drifting, recycled endlessly through the great cycles of matter and energy. There is no rush. There is no deadline. The universe is patient, and tonight you can be patient too. Let the facts settle in your mind like grains settling in a cloud. Slowly, gently, without force. You do not need to hold on to them. You do not need to understand everything perfectly. The details will still be there tomorrow, waiting quietly in the structure of the cosmos. The universe is not empty. It is full of tiny solid particles floating silently, shaping the darkness and the light, making new worlds possible. And as you lie here, breathing slowly, feeling the weight of your body easing into rest, you are connected to that vastness, made of the same elements, shaped by the same processes, part of the same unbroken chain that leads from dust to stars to planets to this moment, right now where sleep is beginning to arrive on its own. The next story is about to begin. Please relax and enjoy. A comet is a small object moving through our solar system, and at its most basic level, it's made of ice, dust, and rocky material. When you picture what a comet actually is, you might imagine something bright and dramatic streaking across the sky, but the physical object itself, the actual solid part, is often quite modest in size. Scientists sometimes describe comets as dirty snowballs, though this phrase doesn't tell the whole story. Many comets are better thought of as icy, dusty, somewhat fragile rocks. They're not perfectly round balls of clean snow. They're irregular, lumpy ancient objects that have been drifting through space for billions of years, carrying within them a mixture of frozen water, frozen gases, tiny grains of dust, and bits of stone. The solid centre of a comet, the part that actually exists as a single piece, is called the nucleus. And when we talk about the nucleus, we're talking about something that might be surprisingly small compared to what you see when a comet becomes visible in the night sky. Many comet nuclei are only a few kilometers across. To give you a sense of scale, that's roughly the size of a small city or a large town. You could walk across the surface of many comet nuclei in an hour or two if you were able to stand on one, though of course you'd be standing on something extremely cold, covered in dark dust and utterly silent in the vacuum of space. For most of its journey through the solar system, a comet looks quite faint. It doesn't announce itself, it doesn't glow on its own. It's simply a small, dark object moving along its orbit, too dim for most telescopes to notice unless someone is specifically looking for it. But something changes when a comet gets closer to the sun. As sunlight begins to warm the surface of the nucleus, something quiet and beautiful begins to happen. The ice on and just below the surface of the comet doesn't melt the way ice melts on Earth. Instead, it sublimates. Sublimation is the process where a solid turns directly into a gas without passing through a liquid phase first. On Earth, you can see this happen with dry ice, which is frozen carbon dioxide. Leave dry ice out on a table and it doesn't form a puddle. It simply releases vapor and disappears. The same thing happens on a comet. The frozen water, frozen carbon dioxide, frozen carbon monoxide, and other ices trapped in the nucleus begin to turn into gas when the sun's warmth reaches them. That escaping gas doesn't just vanish into space, it carries something with it. As the gas rises from the surface, it lifts fine dust particles that were mixed in with the ice or resting on the comet's surface. This creates a cloud of gas and dust around the nucleus, and this cloud has a name: the coma. The coma is the fuzzy glowing envelope that surrounds the tiny nucleus, and it can become much, much larger than the nucleus itself. Even if the nucleus is only a few kilometers wide, the coma can swell to become tens of thousands or even hundreds of thousands of kilometers across. Suddenly, a small object becomes something vast and diffuse. The coma is what makes comets look like they have a soft glow when you observe them through a telescope, or, if the comet is bright enough, with your own eyes. It's not a sharp, hard object. It's a gentle cloud of particles and molecules illuminated by sunlight, spreading outward in all directions from the hidden nucleus at the center. The process of creating a coma is gradual and responsive to changing conditions. As the comet continues to approach the sun, the intensity of sunlight increases, and with it, the rate of sublimation. More ice turns to gas, more dust is lifted, and the coma grows larger and brighter. This isn't a violent process, not an explosion or a sudden release. It's more like a slow exhalation, a steady breathing out of material that has been locked in ice for eons. The gas molecules that escape from the nucleus are moving at speeds determined by their temperature, spreading outward in all directions, carrying dust grains along with them. Some of these molecules and dust grains will eventually be pushed away into the comet's tail. Others will simply disperse into space, adding to the thin scattering of matter that exists between the planets. But the coma is not the only feature a comet can develop. Many comets also grow tails, and here's where things become even more interesting. A comet's tail is not necessarily a single structure. Comets can have more than one kind of tail, and each kind forms for a different reason. Many comets develop what's called a dust tail. This tail is made of fine grains of dust that were lifted off the nucleus by the escaping gas. Once these dust particles are free in space, they don't just sit still. They're pushed outward by the gentle but persistent pressure of sunlight. Yes, sunlight has pressure. Photons, the particles of light, carry momentum, and when they strike a dust grain, they give it a tiny push. Over time, those tiny pushes add up, and the dust gets blown away from the comet in a broad, curving tail. The dust tail often looks softer and more diffuse than other structures around the comet, and because the dust particles are heavy enough to be influenced by the comet's own motion through space, the dust tail tends to curve slightly, tracing a gentle arc. The pressure of sunlight is extraordinarily faint by everyday standards. You don't feel sunlight pushing on you when you stand outside on a sunny day because the pressure is so small. But in space, where there's no air resistance and objects can be very light, even this faint pressure can have significant effects over time. Dust grains released from a comet are small and have very little mass, so the accumulated push from millions of photons striking them can gradually alter their trajectory. The smallest, lightest grains are pushed the most, while larger, heavier grains are pushed less. This creates a sorting effect in the dust tail, with different sized particles spreading out along slightly different paths, contributing to the tail's broad, fan-like appearance. Many comets also form an ion tail. An ion is an atom or molecule that has lost or gained electrons, giving it an electric charge. When the sun releases a stream of charged particles, mostly electrons and protons, this stream is called the solar wind. The solar wind rushes outward from the sun in all directions, travelling at speeds of hundreds of kilometers per second, and when it encounters the gas in a comet's coma, it can strip electrons from the gas molecules, turning them into ions. These ions are now electrically charged, and because they're charged, they respond to the magnetic field carried by the solar wind. The solar wind sweeps these ions directly away from the sun in a straight line, creating what's called the ion tail. The ion tail often looks straighter and narrower than the dust tail. It's usually blue or cyan in colour in photographs because the ions often include molecules like carbon monoxide, which glow in specific colours when they're energised by sunlight. The dust tail, by contrast, appears yellowish or white because it's simply reflecting sunlight off tiny particles. The interaction between the solar wind and a comet's ion tail is complex and dynamic. The solar wind carries with it the sun's magnetic field, which is frozen into the flow of charged particles. When this moving magnetic field encounters the ionized gas around a comet, it drapes around the coma and stretches out into a long, narrow tail. The ions are trapped in the magnetic field and carried away at high speed. This process is efficient and fast, which is why the ion tail can extend to enormous lengths, sometimes stretching for tens of millions of kilometers, far longer than the orbit of Mercury. The ion tail is also more responsive to changes in the solar wind than the dust tail. When the sun releases a particularly strong burst of solar wind called a coronal mass ejection, the ion tail can brighten suddenly, twist, or even break off entirely in a disconnection event. Here's something that surprises many people when they first learn about comets. A comet's tails generally point away from the sun, not behind the comet like a trail. If you imagine a comet as a car driving down a road, you might think its tail would stream out behind it the way your hair streams behind you when you ride a bike. But that's not what happens. The tails point away from the sun because they're being pushed by sunlight pressure and by the solar wind, not by the comet's motion through space. This means that as a comet approaches the sun, its tail can actually trail behind it. But as the comet swings around the sun and begins to move away, the tail goes first, pointing outward ahead of the nucleus as the comet retreats back into the cold outer solar system. The comet, in a sense, can move tail first on part of its journey. Sometimes a comet can appear to have multiple streamers or a fan shape, especially if you're looking at it with very sensitive instruments. The structure of a comet's tail can be complex, shaped by the interaction of dust, ions, magnetic fields, and the comet's rotation. Different viewing angles can make the same comet look quite different. If you're viewing a comet from an angle where you're looking along the plane of its orbit, the tail might appear very long and dramatic. If you're viewing it from above or below its orbital plane, the tail might appear shorter or more spread out. The three-dimensional structure of a comet and its tails can be challenging to visualize from a two-dimensional photograph or from our vantage point on Earth. Astronomers sometimes use multiple observations from different locations or times to reconstruct what the comet's tail structure really looks like in space. The nucleus itself is usually too small to see directly, even in powerful telescopes. Most of what we notice when we look at a bright comet is the coma and the tail. The actual icy, rocky body at the heart of it all might be just a few pixels in even the best images, or completely invisible. Yet that tiny nucleus is the source of everything. All the gas, all the dust, all the glowing beauty of a comet comes from this small, fragile object, losing pieces of itself bit by bit as it travels near the sun. Comet tails can change from night to night as the comet rotates and releases jets of gas and dust from different areas on its surface. If you watch a comet carefully over several nights, you might notice that its tail shifts shape, or that streamers appear and fade. This is the comet responding to the changing angle of sunlight on its rotating surface and to variations in the solar wind. A comet can look dramatic and otherworldly, even though fundamentally it's simply sunlight interacting with dust and gas in the most straightforward physical way. There's something meditative about the way a comet changes over the course of its approach to the sun. It starts as a faint point of light, barely distinguishable from distant stars. Gradually, night after night, it brightens. A fuzzy halo appears around it, the developing coma. Then, if conditions are right, a faint tail begins to emerge, at first just a slight elongation, then growing longer and more distinct. The comet reaches its peak brightness around the time it passes closest to the sun, and then, as it moves away, the process reverses. The tail fades, the coma shrinks, the brightness diminishes, and eventually the comet returns to being just a faint point, then disappears from view entirely. This cycle can take weeks or months depending on the comet's orbit and how close it comes to Earth and the sun. Watching this slow transformation is like watching a flower bloom and fade, except the timescale is stretched out and the flower is made of ice and dust and is millions of kilometers away. Comets travel on orbits around the sun just like planets do. They're part of the solar system, bound by the sun's gravity, moving along paths that are determined by the same laws of motion and gravitation that govern everything from falling apples to orbiting moons. But while planets move on nearly circular orbits, many comet orbits are very stretched out. They're long oval paths called ellipses, and some of these ellipses are so elongated that a comet might spend the vast majority of its time far, far from the sun, only briefly sweeping close before retreating again. Comets are often grouped into two broad categories based on how long they take to complete one orbit: short-period comets and long-period comets. Short-period comets are those that return to the inner solar system relatively frequently, typically in under about 200 years. These are the comets we can predict. We know when they'll return. We can track them over multiple passages. Long-period comets, on the other hand, can take thousands of years to complete a single orbit. Some of them may take hundreds of thousands of years, or even longer. For these comets, recorded history covers only a tiny fraction of their journey. Some comets may only visit the inner solar system once in all of human history, before leaving again on a path that will take them back to the outer reaches for millennia. The shape of a comet's orbit tells you something about its history. A very elongated orbit suggests that the comet originated far from the sun and was perturbed inward by some gravitational interaction. A less elongated orbit might indicate that the comet has been nudged by planets over multiple passes, gradually having its orbit altered into something shorter and more circular. The details of orbital mechanics are fascinating in their precision. Once you know a comet's position and velocity at a particular moment, you can calculate where it will be at any point in the future or where it was at any point in the past, limited only by the accuracy of your measurements and the complexity of accounting for all the gravitational influences acting on it. A comet's closest point to the sun is called perihelion. This is the moment when the comet is most affected by the sun's heat and gravity. It's at perihelion that a comet usually becomes most active, releasing the most gas and dust, growing its brightest coma and longest tails. The farthest point in a comet's orbit from the sun is called aphelion. At aphelion, a comet is cold and quiet. If it's far enough out, it might be completely frozen, inactive, indistinguishable from any other small icy body drifting in the dark. Near perihelion, a comet is usually at its brightest because the increased heating makes the sublimation process much more vigorous. More ice turns to gas, more dust gets lifted away, the coma swells larger, and the tails grow longer and more visible. But this also means that every time a comet passes close to the sun, it loses a little bit of itself. The ice sublimates away and doesn't come back. The dust drifts off into space. Slowly, orbit by orbit, a comet sheds mass. The amount of material a comet loses during each passage can vary greatly. A very active comet might lose millions of tons of material. A less active comet might lose much less. Over many orbits, this loss adds up. Eventually, a comet can lose so much mass that it becomes much less active, or it can even run out of volatile material entirely. Some comets have been observed to fade over multiple returns, becoming progressively dimmer and less active as their supply of ice diminishes. The surface of a comet can also change in ways that affect its activity. As ice sublimates, non-volatile materials, dust and rocky particles, can accumulate on the surface, forming a crust that insulates the ice beneath. This crust can slow down or even halt sublimation from some areas, reducing the comet's overall activity. However, fresh ice can be exposed through impacts, through thermal stress cracking the crust, or through the collapse of surface features, leading to renewed activity. Comets can be nudged over time by the gravity of planets, especially Jupiter. Jupiter is by far the most massive planet in our solar system, and its gravitational influence is strong. When a comet passes near Jupiter, even if it doesn't come particularly close, Jupiter's gravity can tug on the comet and change its orbit. A comet that was on a long-period orbit might get pulled into a shorter orbit. A comet that was already on a short orbit might get thrown onto a different path entirely, or even ejected from the solar system altogether. This gravitational sculpting has been happening for billions of years. Jupiter has likely altered the orbits of countless comets, sometimes capturing them into orbits that bring them near the sun more frequently, sometimes scattering them outward. Because of this, the orbits of comets are not static. They evolve, over time, shaped by the push and pull of the sun and the planets. The gravitational influence of planets on comets is an example of what's called the three-body problem in physics. When you have two objects, say the Sun and a comet, calculating their mutual gravitational interaction and predicting their future positions is straightforward. But when you add a third body, say Jupiter, the problem becomes much more complex. In most cases, there's no simple formula that gives you the answer. You have to use numerical methods, calculating the forces step by step through time. This is why predicting the exact behaviour of comets over very long timescales can be challenging. Small uncertainties in the initial conditions or in the positions of the planets can grow over time, making long-term predictions less reliable. The concept of chaos in physics often comes up in discussions of comet orbits. Chaos, in the scientific sense, doesn't mean randomness or disorder. It means that a system is extremely sensitive to initial conditions. A tiny change in the starting position or velocity of a comet can lead to vastly different outcomes over millions of years. This doesn't mean we can't predict anything about comets, but it does mean that there are limits to how far into the future or the past we can accurately trace their orbits. For short-period comets observed over a few orbits, predictions can be very accurate. For long-period comets, or for trying to trace a comet's path millions of years back, uncertainty grows. Many short-period comets are linked to a region of the solar system called the Kuiper Belt, which lies beyond Neptune. The Kuiper Belt is a region filled with icy bodies and small worlds, remnants from the early solar system that never gathered together to form a planet. It's a vast, cold place where objects can be made mostly of ice and rock, preserved in the deep freeze of the outer solar system for billions of years. Some of these Kuiper Belt objects get nudged by gravitational interactions or collisions and fall inward toward the Sun, becoming the short-period comets we observe. The Kuiper Belt is home to many fascinating objects, including dwarf planets like Pluto, Eris, Makemake, and Haumea. These are worlds in their own right, but they share the same icy composition as comets, differing mainly in size. But there's another source of comets, one that's even more distant and more mysterious. Some comets are thought to come from a region called the Oort cloud. The Oort cloud is a hypothesized vast, distant shell of icy objects that surrounds the solar system at an enormous distance. If the Oort cloud exists as scientists believe, it would be far, far beyond the Kuiper Belt, so far that it would take light from the Sun many hours or even days to reach its outer edges. The Kuiper Belt extends from about 30 astronomical units from the Sun to perhaps 50 or 60. An astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometres. The Oort cloud, by contrast, is thought to extend from perhaps 2,000 astronomical units out to as far as 100,000 astronomical units or more. At those distances, the Sun would appear as just a bright star, not the blazing disk we see from Earth. The Oort cloud hasn't been directly observed because the objects in it are too small and too far away to see, even with our best telescopes. But we infer its existence from the comets we do see. Long-period comets come from all directions in the sky, not just from the plane where the planets orbit. This suggests that there's a roughly spherical cloud of icy objects surrounding the Sun at a great distance, and occasionally something disturbs one of those objects and sends it falling inward. What could disturb an object that far out? Passing stars, for one. Even though space is vast and mostly empty, stars do pass relatively close to the Sun from time to time over millions of years. A star passing within a few light years of our solar system could gravitationally nudge objects in the Oort cloud, changing their orbits just enough to send them drifting inward. The gentle pull of the galaxy itself, the tidal forces from the combined mass of all the stars in the Milky Way, can also disturb faraway icy bodies over very long timescales. The idea of the Oort cloud came from the work of Dutch astronomer Jan Oort in the 1950s. He studied the orbits of long-period comets and noticed that many of them seemed to have their aphelia, their farthest points from the Sun, at similar, very large distances. This suggested that there was a reservoir of comets at that distance, and that comets entering the inner solar system for the first time were being perturbed from this reservoir. The Oort cloud is thought to contain billions or even trillions of icy objects, though most of them are quite small. The total mass of the Oort cloud is uncertain, but might be only a few times the mass of Earth, spread out over an enormous volume of space. So a comet, in a sense, can be like a message from the solar system's outermost edges. It spent billions of years in the cold and dark untouched, and then some subtle gravitational nudge set it on a path that would eventually bring it close to the Sun and into view of observers on Earth. Comets may preserve very old material from the early solar system. When the solar system was forming, about 4.5 billion years ago, there was a disk of gas and dust surrounding the young Sun. Planets formed from this disk, growing larger and larger as they swept up material. But not everything got incorporated into planets. In the outer parts of the solar system, where it was cold enough for water and other compounds to freeze, there were countless small icy bodies. Some of these became moons, some clustered in the Kuiper belt, and some were flung outward to form the Oort cloud. Because these objects formed so far from the Sun and have remained cold ever since, they haven't been significantly altered by heat or chemical reactions. They're like time capsules. Studying comets helps scientists learn what the solar system was like long ago, what materials were present in the early disk, what chemical processes were happening, and how planets like Earth eventually came to have water and organic molecules. The early solar system was a chaotic place. The disk of gas and dust that surrounded the young Sun was turbulent, with materials spiralling inward, colliding, sticking together, and sometimes being thrown outward. Temperature varied with distance from the Sun. Close to the Sun, it was hot enough that only rocky and metallic materials could condense into solid particles. Farther out, beyond what's called the frost line or snow line, it was cold enough for water ice to form. This is why the inner planets, Mercury, Venus, Earth, and Mars, are rocky, while the outer planets, Jupiter, Saturn, Uranus, and Neptune, are gas and ice giants. The frost line was a crucial boundary in the forming solar system, and comets originated beyond it, in the cold regions where ice was stable. When spacecraft have visited comets and analysed their composition, they've found a remarkable variety of materials. Comets contain not just water ice, but also frozen carbon dioxide, carbon monoxide, methane, ammonia, and many other compounds. They contain complex organic molecules, the building blocks of chemistry that can lead to life. None of this means comets themselves are alive or that life came from comets in some direct way, but it does mean that comets carried raw ingredients that might have been delivered to the early Earth through impacts, contributing to the mix of chemicals that eventually led to the emergence of life. It's a humbling thought. The water in Earth's oceans, the carbon in your body, might have ridden through space on countless small comets and icy asteroids that crashed into our planet billions of years ago. Earth's water is something of a mystery. Our planet is rocky and formed relatively close to the Sun, yet it has vast oceans. Where did all that water come from? One possibility is that it was delivered by comets and asteroids after Earth had mostly formed. During a period called the Late Heavy Bombardment, roughly 4 billion years ago, the inner solar system experienced an intense period of impacts. Comets and asteroids from the outer solar system rained down on the inner planets. Some of these impacts would have brought water and organic molecules to Earth. How much of Earth's water came from comets versus asteroids is still debated. Studies of the isotopic composition of water in comets, specifically the ratio of deuterium, a heavy form of hydrogen, to normal hydrogen, have shown that some comets have water with a different isotopic signature than Earth's oceans. This suggests that while comets might have contributed some of Earth's water, much of it may have come from asteroids which have water that more closely matches Earth's. A comet nucleus is typically very dark because the dust on its surface absorbs most of the light that hits it. When scientists finally got close-up images of comet nuclei from space missions, one of the surprising discoveries was just how black they are. Many comet nuclei have very low reflectivity, much darker than you might expect for something made mostly of ice. Why is this? The surface of a comet gets coated with a layer of dark dust as ice sublimates away. Ice is bright and reflective, but dust, especially carbon-rich dust, is dark. Over time, as a comet makes repeated passes near the Sun, the surface ice sublimates and escapes, but the dust is often too heavy to be lifted away by the gentle flow of gas. It accumulates, forming a crust. This crust can insulate the ice beneath, making the sublimation process more complex. Gas has to work its way up through cracks and vents in the crust. This is why comets can have jets, streams of gas and dust escaping from active spots where the crust is thinner or broken. The dark surface of comets surprised early researchers who expected to see bright, icy surfaces. The reflectivity, or albedo, of many comet nuclei is only a few percent. meaning they reflect only a tiny fraction of the sunlight that hits them. This is comparable to the reflectivity of asphalt or charcoal. The darkness comes from organic compounds, carbon-rich materials that formed in the early solar system, mixed with silicate dust. These materials have been processed by radiation over billions of years, further darkening them. The dark surface also means that comets can heat up more than you might expect when they're near the sun, because dark materials absorb heat more efficiently than bright ones. Jets can make a comet's brightness flicker and shift over the course of hours or days. As a comet rotates, different areas of its surface are exposed to sunlight at different times. An area that was in shadow and inactive might rotate into sunlight and suddenly begin releasing gas and dust, creating a new jet. An area that was active might rotate into shadow and go quiet. This rotation, combined with the irregular shape of many comet nuclei, means that the activity of a comet is rarely uniform or steady. It pulses and shifts in a complex dance of light, shadow, rotation, and sublimation. Some comet nuclei are very irregular and lumpy rather than round. They can look like potatoes or dumbbells or jagged rocks. Some comets are actually two or more pieces loosely bound together by their own faint gravity, tumbling through space as a fragile pair or cluster. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, has a distinctive two-lobed shape that makes it look like a rubber duck. This shape might have resulted from two separate objects gently colliding and sticking together, or from uneven erosion over time. The rotation of comets can be complex. Some comets tumble, rotating around multiple axes at once. Others have relatively simple rotation, spinning around a single axis like a top. The rotation can change over time due to the uneven forces from jets pushing on different parts of the surface. This is called non-gravitational acceleration, and it can cause a comet's rotation to speed up, slow down, or change its orientation. Understanding a comet's rotation is important for predicting its behavior and for planning spacecraft missions, because the activity and hazards around a comet depend on which areas are active and when. Comets can crack, fragment, or break apart, especially after repeated trips near the sun. The heating and cooling cycle, the stress of rotation, the loss of mass, all of this can weaken a comet's structure. Sometimes a comet will simply split into two or more pieces, which then travel along slightly different orbits. When a comet loses enough material over many orbits, it can fade into a quieter object over time, no longer producing a visible coma or tail, eventually becoming what's called a dormant or extinct comet, or even just a rocky asteroid-like body that no longer shows any sign of ice. Some asteroids in the inner solar system might actually be the rocky remains of ancient comets that have completely lost their volatile materials. Distinguishing between a true asteroid and an extinct comet can be difficult without detailed analysis of the object's composition and orbit. A comet's life is often a slow process of change, shedding, and return. Each passage near the sun erodes it a little more. Each orbit brings it back, a little smaller, a little less active. For some comets, this cycle can continue for thousands of years. For others, the end comes more quickly. They break apart, or they're perturbed onto a collision course with the sun or a planet, or they're ejected from the solar system entirely by a close encounter with Jupiter. There's a kind of gentle tragedy in the life of a comet. It's beautiful because it's dying, slowly giving itself away to space with each close approach to the sun. But there's also a kind of patience to it. A comet doesn't rush. It follows its orbit year after year, century after century, pulled by gravity along a path it cannot deviate from except by chance encounters. It's a traveller that keeps returning, as long as it lasts. One of the most famous returning comets is Halley's Comet, which completes an orbit roughly every 75 to 76 years. This means that Halley's Comet appears in the inner solar system about once per human lifetime, making it possible for someone to see it twice if they live long enough and are lucky with timing. Halley's Comet has been recorded by observers for centuries, with documented sightings going back over 2,000 years. Ancient Chinese astronomers recorded it. European monks noted it in medieval chronicles. Artists in the Renaissance included it in paintings. The comet appeared in 1066, the year of the Norman conquest, and was later depicted in the Bayeux Tapestry. It returned in 1301, and the Italian painter Giotto may have used it as the model for the Star of Bethlehem in one of his frescoes. It came back in 1456, in 1531, in 1607, in 1682, in 1758, in 1835, in 1910, and most recently in 1986. Each return is an opportunity for a new generation to see the same object their ancestors saw, moving along the same ancient path. The predictability of Halley's comet was a significant achievement in the history of astronomy. When Edmund Halley calculated its orbit and predicted its return in 1758, he was demonstrating that comets obeyed the same natural laws as planets. They weren't supernatural or divine signs. They were physical objects moving through space according to the laws of gravity and motion. This was part of a broader shift in human understanding during the scientific revolution, when natural phenomena that had once been attributed to gods or magic were explained through physics and mathematics. Halley himself didn't live to see the comet's return. He died in 1742, but his prediction was vindicated, and the comet was named in his honour. A bright comet can become part of art and history simply because people notice it together. It's a shared experience, something unusual in the sky that everyone can see, something that doesn't fit the normal pattern of stars and planets. In eras before artificial light drowned out the night sky, a bright comet would have been unmistakable, a glowing visitor that grew night by night, its tail stretching across the heavens. People tried to interpret comets as omens or signs. They didn't know what comets were, but they knew they were something different, something that came and went according to no calendar they understood. Ancient sky watchers often kept careful records of comets' positions, their brightness, the length and direction of their tails. These records, preserved in old manuscripts and inscribed on stone, are valuable to modern astronomers. By comparing ancient observations with current knowledge of comet orbits, scientists can sometimes identify which historical apparition corresponds to which known comet, tracing its path back through history. Chinese astronomical records are particularly valuable for this kind of historical research. Chinese astronomers kept detailed records of celestial events for thousands of years, including comets, novae, and other phenomena. These records are sometimes more complete and systematic than European records from the same periods. By analysing these old observations, astronomers can verify the orbits of known comets, discover previously unknown periodic comets, and study how comet activity has changed over time. Comets helped early astronomers realise the sky is not perfectly unchanging. For a long time, influenced by ancient Greek philosophy, many scholars believed the heavens were eternal and immutable, that only the Earth experienced change and decay. Comets challenged this view. Here were objects that appeared, changed, and disappeared. They moved against the background of stars. In the 16th century, the astronomer Tycho Brahe carefully measured the position of a bright comet and determined that it must be farther away than the Moon. This was significant because it meant that change was happening in the celestial realm, not just in the earthly one. Later, Edmund Halley used Isaac Newton's newly developed laws of motion and gravitation to calculate the orbits of comets recorded in historical records, and realised that the comets of 1531, 1607, and 1682 were actually the same object returning on a roughly 76-year cycle. He predicted it would return in 1758. Halley didn't live to see it, but the comet did return as predicted, and it was named in his honour. This was powerful evidence that comets were natural objects following predictable laws, not supernatural omens. Tycho Brahe's measurements were revolutionary because they used parallax, the apparent shift in position of an object when viewed from different locations. Tycho measured the comet's position from his observatory and compared notes with other astronomers across Europe. If the comet had been close to Earth, below the Moon, its position against the background stars would have shifted noticeably when viewed from different places. But Tycho found no such shift, meaning the comet was much farther away, out among the planets. This shattered the old Aristotelian belief that comets were atmospheric phenomena, weather in the upper air rather than celestial objects. Not every comet becomes bright and famous. Many are only visible with telescopes, faint smudges of light that never develop prominent tails or large comas. Some comets are discovered and catalogued and never seen again because their orbits take them back out into the distant solar system for thousands of years. Comets are often given designations that include letters and numbers. A comet discovered before it's confirmed to be periodic might be designated with C, followed by the year, and a code indicating when in that year it was found. If the comet is confirmed to orbit the Sun with a period of less than 200 years, it's given a P designation and a number like P1 for Halley's Comet, the first periodic comet recognised. Comets can also be named after their discoverers, sometimes with multiple names if multiple people independently found the same comet. In the modern era, many comets are discovered by automated sky surveys that scan the sky night after night, looking for anything that moves or changes. These surveys have names like Pan-STARRS, Linear or SOHO, and comets found by them often carry those names. The naming conventions for comets have evolved over time. In the past, comets were often named after the person or people who discovered them, sometimes leading to comets with multiple names if several observers found it independently. Now the naming is more systematic. The designation tells you about the comet's type and when it was discovered, and the name typically acknowledges the discoverer or the survey that found it. For example, Comet C2020F3, Neowise, was a comet discovered in 2020 during the first half of March, designated by the letter F, was the third comet discovered in that period, hence the number 3, and was found by the Neowise Space Telescope. A comet's brightness depends on many factors: the size of its nucleus, how active it is, how close it comes to the Sun, how close it comes to Earth, and the angle at which we view it. Even a relatively small comet can look grand if it happens to pass close to Earth, and develops a large coma and long tail. Conversely, a large comet that stays far from both the Sun and Earth might remain faint and unimpressive. Predicting how bright a comet will become is notoriously difficult because it depends on how much gas and dust the comet will release, and that can vary unpredictably. Some comets have been expected to put on spectacular shows and then fizzled, releasing less material than predicted. Others have surprised astronomers by becoming brighter than expected. Comets are individuals. Each one has its own composition, its own structure, its own history of heating and cooling, and these differences mean that each comet behaves a little differently when it approaches the Sun. Comet Eson in 2013 was a good example of a comet that didn't live up to expectations. Early predictions suggested it might become extremely bright, perhaps even visible during daytime. But as it approached the Sun, it became clear that it wasn't releasing as much material as hoped, and then, as it passed very close to the Sun, it disintegrated entirely. What had been anticipated as the comet of the century ended up being a disappointment for many observers, though scientifically it was still valuable to watch a comet break apart under extreme conditions. Conversely, Comet Hale-Bopp in the late 1990s exceeded expectations, becoming one of the brightest and most widely observed comets of the 20th century, visible to the naked eye for many months. The unpredictability of comets is part of their charm and part of the challenge for astronomers. Unlike planets, whose positions can be predicted with extraordinary precision centuries in advance, comets can surprise you. They can brighten suddenly, or fade, or split apart. Each comet is a unique object with its own behaviour, and part of the excitement of comet astronomy is that you never know quite what you're going to get. As comets travel along their orbits, they can leave behind trails of dust. This dust doesn't disappear. It continues to orbit the Sun along a path similar to the comet's orbit, spreading out over time into a long stream that follows the comet's path like a river of invisible particles. When Earth, in its own orbit around the Sun, crosses one of those dust streams, something beautiful happens. We get a meteor shower. A meteor is what you see when a tiny grain of dust or a small pebble enters Earth's atmosphere at high speed and burns up due to friction with the air. The grain itself is often smaller than a grain of sand, but it's moving so fast, tens of kilometers per second, that when it hits the atmosphere, it heats the air around it to thousands of degrees. The air glows, and we see a brief streak of light across the sky. A shooting star, though it's not a star at all, just a bit of comet dust meeting its end in a brilliant flash. The speed at which meteor particles hit Earth's atmosphere depends on several factors, including the relative velocity of Earth and the dust stream. Earth orbits the Sun at about 30 kilometers per second. If a dust particle is also orbiting the Sun in the same direction as Earth, but at a different speed, the collision speed is the difference between the two velocities. If the particle is moving opposite to Earth's motion, the speeds add together, leading to much higher impact velocities. This is why some meteor showers produce faster meteors than others. The Leonids, for example, are known for producing very fast meteors because Earth runs almost head-on into the dust stream from Comet Tempel-Tuttle. Many meteor showers happen around the same time each year because Earth meets the same dust stream again and again as it orbits the Sun. The geometry is predictable. Earth crosses a particular point in its orbit on the same date each year, and if there's a stream of comet dust at that point, we'll see meteors. The Perseid meteor shower, one of the most reliable and popular meteor showers, happens every August when Earth crosses the orbit of comet Swift-Tuttle. The dust left behind by Swift-Tuttle over many orbits creates a stream, and when Earth ploughs through that stream, we see dozens of meteors per hour radiating from the constellation Perseus. The Leonid meteor shower in November is linked to comet Tempel-Tuttle. The Geminids in December are linked to an object called 3200 Phaethon, which might be an extinct comet or a rock-comet hybrid. Each shower is a gentle reminder that space is not empty. It contains small drifting particles, the remnants of comets that passed by long ago. The Geminids are particularly interesting because their source, 3200 Phaethon, doesn't behave quite like a typical comet. It's classified as an asteroid, but it has an orbit that brings it very close to the Sun, and it shows some faint activity that might be the release of the dust. Some researchers think Phaethon might be a rock comet, an object that once had ice but has lost most or all of it, leaving behind a rocky remnant that still releases a little dust when heated. This blurs the line between asteroids and comets, suggesting that these categories aren't as distinct as we once thought. Most comet dust grains are very small, often the size of sand or smaller. A grain of rice would be considered large, yet these tiny particles moving at cosmic speeds create visible streaks of light when they encounter our atmosphere. The bright streak you see is mostly the air itself glowing from heat, not the grain on fire. The dust grain heats the air in front of it, compressing and ionizing it, and that hot glowing air is what you see as the meteor trail. Often the dust grain itself vaporizes completely in a fraction of a second, never reaching the ground. Only larger pieces, small rocks or bits of metal can survive the journey through the atmosphere and land as meteorites. The vast majority of meteors from comet dust streams burn up entirely, adding a tiny bit of vaporized material to Earth's upper atmosphere. Over the course of a year, Earth sweeps up thousands of tons of cosmic dust, most of it from comets. It settles slowly through the atmosphere, eventually making its way to the ground as fine particles mixed into the air and soil. You've probably breathed in a few atoms that were once part of a comet. This constant influx of cosmic dust is one of the ways Earth continues to gain mass, even billions of years after it formed. The amount is tiny compared to Earth's total mass, but it's a steady drizzle of material from space. Scientists collect cosmic dust from high-altitude aircraft, from ice cores in Antarctica, and from the deep ocean floor. Studying this dust gives insights into the composition of comets and asteroids, and into the history of the solar system. A meteor shower is like Earth passing through a quiet, invisible sprinkle of comet dust. The meteors seem to radiate from a single point in the sky, called the radiant, but this is an effect of perspective. The dust grains are all travelling along parallel paths, but because of the way we view them from Earth's surface, they appear to diverge from a point, much the way parallel railroad tracks seem to converge at a distant point. If you were to trace back the paths of all the meteors in a shower, they'd point back to the same spot in the sky. That spot is named after the constellation it's in, which is why we have the Perseids from Perseus, the Leonids from Leo, the Geminids from Gemini, and so on. Watching a meteor shower is a peaceful experience. You lie on your back, look up at the sky, and wait. Every few minutes, a streak of light flashes across your field of view. Each streak is a fragment of a comet, a tiny traveller ending its journey. It's a connection across time and space. You're seeing the last moment of something that might have been orbiting the Sun for thousands or millions of years. The best meteor showers can produce dozens or even over 100 meteors per hour under ideal conditions, though you need dark skies away from city lights to see the fainter ones. The experience of watching a meteor shower is different from looking at planets or stars through a telescope. There's no instrument between you and the sky. You're just there, under the stars, part of the turning Earth as it moves through space, and the meteors are a direct, visceral reminder that you're on a planet moving through a solar system that's full of debris from ancient comets. Spacecraft have flown past comets to take close images and measurements, and each mission has revealed new details about these ancient objects. The Giotto mission, launched by the European Space Agency, visited Halley's Comet in 1986 during its most recent return. Giotto flew within about 600 kilometers of the nucleus, close enough to take detailed images and measurements, even as it was battered by dust particles. The images from Giotto showed that Halley's nucleus was shaped like a lumpy peanut, dark and cratered, with bright jets of gas and dust erupting from specific areas on the sunlit side. It was the first time humanity had seen the nucleus of a comet up close, and it was both familiar and alien, a small, battered rock in space, yet also the source of the beautiful coma and tail that had been observed for millennia. Giotto's encounter with Halley's comet was hazardous. The spacecraft was travelling at about 70 kilometers per second relative to the comet, and at that speed, even a tiny dust grain hits with enormous energy. Giotto's camera was damaged by a dust impact during closest approach, causing the images to go dark for a moment before the spacecraft recovered. Despite this, Giotto survived and was later retargeted to fly by another comet, Griggs-Yellerup, in 1992. The fact that spacecraft can survive close encounters with comets at all is a testament to careful engineering and some good fortune. NASA's Stardust mission, launched in 1999, flew by Comet Wild 2 in 2004. Stardust had a special purpose. It carried a collector filled with aerogel, a lightweight, porous material that could capture dust particles without destroying them. As Stardust flew through the coma of Wild 2, tiny dust grains embedded themselves in the aerogel. The spacecraft then returned to Earth in 2006, bringing back the first samples of comet material ever collected and returned. Scientists studying those samples found a surprising mix of materials. Some of the dust grains were made of minerals that form at high temperatures, suggesting they had been forged near the Sun and then somehow transported out to the cold regions where comets form. This hinted at a solar system that was much more dynamic and mixed in its early days than previously thought. Comets, it seemed, were not just pristine lumps of outer solar system ice, but rather mixtures of materials from all over the early solar nebula. Aerogel is a remarkable material, sometimes called frozen smoke, because it's mostly air but solid. It's the best substance known for gently catching fast-moving particles without vaporizing them. When a dust grain hits aerogel at high speed, it burrows into the material, creating a carrot-shaped track. Scientists can then carefully extract the grain from the end of the track and analyze it with powerful microscopes and spectrometers. The Stardust samples revealed organic molecules, tiny crystals of various minerals, and complex structures that showed these dust grains had been through a variety of processes. The Deep Impact mission, launched in 2005, took a more dramatic approach. It sent a small impactor crashing into Comet Tempel 1 at high speed while a nearby spacecraft observed. The idea was to excavate material from below the surface crust and see what was inside. The impact created a bright flash and threw up a plume of dust and gas. Observing the composition of that plume gave scientists insights into the interior of the comet, which turned out to be very fine, fluffy material, almost powder-like rather than solid ice. This suggested that comet nuclei are not dense, hard objects, but rather loosely packed aggregates of ice and dust, more fragile than expected. The impact on Tempel 1 was carefully planned and observed by telescopes on Earth and in space, as well as by the Deep Impact spacecraft itself. The bright flash and plume were visible to ground-based observatories, and data from multiple instruments gave a detailed picture of what was thrown out. The material was rich in fine dust and water vapour, and the comet's interior appeared to be much less dense than solid ice, suggesting a porous, fragile structure. Some scientists describe comet nuclei as more like icy dirt piles than solid rocks. The European Space Agency's Rosetta mission, launched in 2004, was perhaps the most ambitious comet mission to date. Rosetta didn't just fly past a comet, it orbited one. In 2014, after a 10-year journey through the solar system, Rosetta arrived at Comet 67P Churyumov-Gerasimenko, a comet with a strange two-lobed shape that made it look like a rubber duck. Rosetta spent over 2 years orbiting 67P, watching it transform as it approached the Sun, observing jets turn on and off, mapping its surface in detail, and analysing the gases in its coma. Rosetta also deployed a small lander called Philae, which attempted to land on the surface of the comet. The landing was only partially successful. Philae bounced and ended up in a shadowed spot where its solar panels couldn't get enough light. But it still managed to take images and measurements from the surface before its batteries ran out. Philae sent back the first ever photographs taken from the surface of a comet, showing a landscape of boulders, cliffs, and dust under a pitch-black sky. Rosetta's 2-year observation of 67P was unprecedented. The spacecraft watched the comet wake up as it approached the Sun, with activity increasing month by month. Jets would appear and change, sometimes lasting for hours or days, sometimes appearing and disappearing within minutes. Rosetta mapped the entire surface of the comet in high resolution, identifying different terrain types, smooth plains, rough rocky areas, pits and cliffs. The data from Rosetta filled in countless details about how comets work, how their surfaces evolve, how ice and dust interact, and how the solar wind affects the coma and tail. Philae's landing was a dramatic moment. The lander was released from Rosetta and descended slowly toward the surface. But the harpoons designed to anchor it didn't fire properly, and Philae bounced. It touched down, bounced, touched down again, bounced higher, and finally settled in a location that wasn't the planned landing site. The spot was shadowed, so Philae's solar panels didn't get enough sunlight to keep it powered after its primary batteries ran out. But during the hours it was active, Philae sent back images and data, including measurements of the surface material, which turned out to be much harder than expected, almost like ice covered by a layer of dust. Visiting comets helps scientists study their chemistry and structure directly. Missions have shown that comet surfaces can be surprisingly complex and varied, with cliffs, pits, layered terrain, and smooth plains. Some areas are covered in dust, others show exposed ice. The surface can change rapidly as the comet heats up, with new pits opening and cliffs collapsing. Comets contain molecules that include carbon-based compounds, some of them quite complex. Rosetta detected glycine, an amino acid, in the coma of 67P. Amino acids are the building blocks of proteins, essential to life as we know it. Finding them in a comet reinforces the idea that the chemistry of life might be widespread in the universe, that the raw ingredients were being delivered to young planets throughout the solar system's history. Each comet studied up close adds a new piece to the story of our solar system's origins, revealing a little more about the conditions and processes that led to the formation of planets, moons, and eventually life on Earth. The detection of complex organic molecules in comets has profound implications. It suggests that the building blocks of life aren't rare or special, that they form naturally in space under a wide range of conditions. Comets delivered these molecules to the early Earth, and perhaps to other planets as well. While we don't know exactly how life began on Earth, we do know that the raw materials were present early on, and some of them likely came from comets. Comets glow mainly because sunlight reflects off dust and interacts with gas in the coma. The dust scatters sunlight the way dust in Earth's atmosphere scatters sunlight, giving the coma a soft, diffuse glow. The gas in the coma can also fluoresce. Fluorescence is a process where molecules absorb ultraviolet light from the sun and then re-emit that energy as visible light. Different molecules fluoresce at different colours, which is why some parts of a comet's coma or tail can appear greenish, bluish, or reddish in colour photographs. The greenish glow often comes from diatomic carbon or cyanogen molecules. The bluish ion tail comes from ionized carbon monoxide. These colours are usually faint and hard to see with the naked eye, but cameras and spectrographs can capture them, revealing the chemical fingerprints of the gases in the coma. Spectroscopy is one of the most powerful tools in astronomy. By spreading light out into its component colours or wavelengths, scientists can identify which molecules and atoms are present in a comet's coma. Each type of atom or molecule absorbs and emits light at specific wavelengths, creating a unique pattern like a fingerprint. By comparing the observed spectrum of a comet to known spectra of different substances, astronomers can determine what the comet is made of, even from millions of kilometers away. The solar wind can cause the ion tail to ripple and shift quickly. The solar wind is not perfectly steady. It fluctuates with changes in the sun's activity, with gusts and lulls. When a gust of solar wind hits a comet, the ion tail can respond almost immediately, bending or even disconnecting. Sometimes a comet's ion tail can experience what's called a tail disconnection event, where the entire tail appears to break away from the comet and drift off into space while a new tail begins to form. This is often linked to changes in the solar wind's magnetic field. The magnetic field carried by the solar wind can reconnect in complex ways with the magnetic field around the comet's coma, and this reconnection can sever the tail. It looks dramatic in time-lapse images. The comet's tail just detaches and floats away, leaving the comet briefly tailless before activity builds a new one. It's a reminder that comets are not isolated objects. They're constantly interacting with the solar wind, with sunlight, with the magnetic environment of the sun. Tail disconnection events are more common than you might think. They've been observed in many comets, and they provide a visible demonstration of the invisible processes happening around comets. The solar wind is a plasma, hot, ionized gas, and it carries the sun's magnetic field with it. When this field encounters the magnetized plasma in a comet's ion tail, complex magnetic reconnection can occur, similar to what happens in Earth's magnetosphere during magnetic storms. These events are a reminder that space is full of dynamic, changing conditions. Some comets come very close to the sun, and these are called sun-grazing comets. Sun-grazing comets have orbits that bring them extremely close to the sun's surface, sometimes within a solar radius or less. At such close distances, the heating is intense. The comet can suddenly brighten, releasing enormous amounts of gas and dust in a very short time. Many sun-grazing comets don't survive. They break apart under the stress of the heat and tidal forces from the sun's gravity, or they simply evaporate completely, their material dispersed into the solar wind. Some sun-grazing comets are discovered only hours before they plunge into the sun, detected by solar-observing spacecraft that watch the sun's outer atmosphere. These spacecraft have discovered thousands of small comets over the years, most of them sun-grazing comets that appeared briefly and then vanished. The SOHO spacecraft, the Solar and Heliospheric Observatory, has been particularly prolific at discovering sun-grazing comets. Its coronagraph, which blocks the bright disk of the sun to reveal the fainter corona, has spotted thousands of tiny comets plunging toward the sun. Most of these comets are members of what's called the Kreutz group, a family of comets thought to be fragments of a much larger comet that broke apart centuries or millennia ago. Each fragment follows a similar orbit, all of them sun-grazing, and they occasionally appear as they make their final, fatal dive toward the sun. Gravity shapes comet paths, but there are also tiny non-gravitational forces that can affect a comet's orbit. When a comet releases jets of gas, those jets act like little rocket engines. If the jets are not perfectly symmetrical, if they're stronger on one side of the comet than the other, they can give the comet a small push. This push is tiny compared to the pull of the sun's gravity, but over many orbits it can add up. Those tiny pushes can slightly alter a comet's orbit over time, making its return a little earlier or a little later than gravitational calculations alone would predict. Astronomers have to account for these non-gravitational forces when they try to predict exactly when a comet will appear. It's a humbling reminder that even in the precise science of celestial mechanics, comets retain a bit of unpredictability. The rocket effect from jets is called the Yarkovsky effect, or, more specifically for rotating comets, the Yorp effect, Yarkovsky-O'Keefe-Radzievsky-Paddock effect. These effects can not only change a comet's orbit, but also its rotation rate and the orientation of its spin axis. Over thousands of orbits, these tiny forces can have large, cumulative effects, and they're one reason why predicting the long-term behavior of comets is so challenging. Comets remind us that the solar system is dynamic, not frozen in place. Things move, things change, things collide and break apart. The solar system today is not the same as it was a billion years ago, and it won't be the same a billion years from now. Comets are part of that ongoing story of change. Many comets are discovered by automated sky surveys that scan the sky quietly every night, taking image after image, comparing them to previous images to find anything that has moved or changed. These surveys have names like the Catalina Sky Survey, Pan-STARRS, and the Atlas Project. They use relatively small telescopes and sensitive cameras to cover large areas of the sky. Most of the comets discovered today are found by these surveys, not by amateur astronomers peering through eyepieces. Though amateur discoveries still happen from time to time, the surveys generate enormous amounts of data which are processed by computers looking for moving objects. When a new comet is found, its position is measured, and those measurements are sent to the Minor Planet Center, an organization that tracks small solar system bodies. Over time, as more observations come in, astronomers can calculate the comet's orbit and predict where it will go next. The automation of comet discovery has dramatically increased the number of known comets. Decades ago, discovering a comet was a major achievement for an amateur astronomer. Now, automated surveys discover dozens of comets each year, many of them faint objects that would never have been noticed by visual observers. This has been good for science, providing a much more complete census of the comet population, but it has also changed the culture of comet hunting. The romance of patient hours at the telescope, sweeping the sky for a new fuzzy visitor, has largely been replaced by algorithms processing images from robotic telescopes. A comet can be both ordinary physics and still feel deeply magical to watch. There's no contradiction between understanding how something works and being moved by its beauty. Knowing that a comet's tail is just dust and gas pushed by sunlight doesn't make the sight of a bright comet hanging in the twilight sky any less wonderful. If anything, understanding makes it more wonderful, because you realize the scale and the patience involved. You're seeing an object that might be billions of years old, that has traveled distances that are hard to imagine, that is slowly giving itself away to the void, and that will continue on its path long after you're gone. Watching a comet is a way of touching deep time, of connecting to processes that operate on timescales far beyond human lifetimes. There's something humbling about looking at a comet and knowing that it existed long before humans did, that it will continue to exist long after our civilization is gone. Comets move on. Timescales that dwarf human concerns. They don't care about politics, economics, or history. They simply follow their orbits, governed by gravity and momentum, patient travelers on ancient paths. Watching a comet can put your own life in perspective, reminding you that you're a small part of a much larger, much older universe. A comet is mostly harmless distance and time, not a threat, just a traveller. There are sensational stories about comets crashing into planets, and it's true that impacts have happened and will happen again. But the solar system is vast, and the chances of any given comet hitting Earth are extremely small. The last major impact from a comet or asteroid was the event that helped end the age of the dinosaurs 66 million years ago, and events on that scale are rare. Modern sky surveys are designed in part to find and track objects that might pose a risk, and so far none of the known comets are on a collision course with Earth. Most comets pass by at safe distances, visible only as points of light or faint smudges in telescopes, no danger to anyone. The light you see from a comet is sunlight that has taken a small detour through dust and gas. Photons from the sun travel outward in all directions. Some of them strike a comet, bounce off a dust grain, and travel in a new direction, toward Earth. By the time that photon reaches your eye, it might have travelled for 8 minutes from the sun to the comet, and then however long from the comet to Earth. The journey is straightforward, governed by the physics of light and matter, but the result is something beautiful. Seeing a comet is like witnessing the solar system's outer storage briefly drift past our neighbourhood. Most of the icy material in the solar system is stored far away, in the Kuiper belt and the Oort cloud, cold and invisible. Every so often, a piece of that distant storage comes close enough to warm up and become visible, offering a glimpse of what's out there in the dark. The same gravity that holds your feet to Earth also guides comets on their long arcs through space. It's the universal force, the attraction between masses, operating on every scale from the pull between atoms to the pull between galaxies. A comet orbiting the sun is following the same fundamental law that makes an apple fall from a tree or the moon orbit Earth. The equation is simple. The force is proportional to the masses involved and inversely proportional to the square of the distance between them. Yet from that simple equation comes the endlessly varied dance of planets, moons, asteroids and comets, each following its own path, each influenced by the gravitational tugs of everything else. A comet's orbit is a solution to that equation, a trajectory through space that balances speed and distance and the pull of the sun. Every comet orbit is a quiet example of patience. The comet waits in the cold for years, decades, centuries, millennia. Then it falls inward, briefly warming, briefly shining, and then it retreats again. The cycle repeats as long as the comet lasts. There's no hurry, no urgency. The comet doesn't know it's being watched. It doesn't care. It simply follows the path that physics dictates. Yet to us, observing from our brief human timescale, a comet's return can feel like a reunion with an old distant traveller. We mark its appearances. We note them in records. We tell stories about them. We name them after people who found them or studied them. We send spacecraft to visit them. We try to understand them. And all the while, the comet continues on, indifferent, patient, following its orbit. Comets show how something small can create something vast. The nucleus might be only a few kilometers across, yet the coma can swell to hundreds of thousands of kilometers. The tail can stretch for millions of kilometers, sometimes longer than the distance from the Earth to the Sun. A tiny object through the simple process of sublimation and the interaction with sunlight and the solar wind can create a structure larger than planets. It's a reminder that size and impact are not always directly related. A small thing, under the right conditions, can become something grand and visible and important. Many of the atoms in comet ice are as old as the early solar system. When the solar system formed from a collapsing cloud of gas and dust, the atoms that would eventually become the Sun, the planets, and the comets were all mixed together in that cloud. The hydrogen in comet ice might have been forged in the Big Bang, the birth of the universe itself, 13.8 billion years ago. The oxygen might have been made inside a massive star that exploded as a supernova billions of years ago, scattering its elements into space where they would eventually become part of the cloud that formed our solar system. The carbon, the nitrogen, the metals, all of them have their own ancient histories. A comet is a collection of ancient atoms that have been on a long journey through time and space, and now they're here, drifting past our planet, briefly visible before moving on. The atoms in your body have similar histories. The carbon in your cells was made in stars. The oxygen you breathe was forged in stellar furnaces. The iron in your blood was created in supernova explosions. You and comets are made of the same stuff, shaped by the same processes, part of the same cosmic story. Comets are messengers carrying information about where we came from, what we're made of, and how the universe works. They're small, cold, fragile objects, but they connect us to the deepest questions about existence and origins. The universe doesn't rush its stories. It tells them in slow cycles, in orbits that take thousands of years, in processes that unfold over billions of years. Stars form, shine for millions or billions of years, and die. Galaxies collide over hundreds of millions of years. Planets migrate, moons form and are destroyed. Comets fall inward and are lost. Everything happens in its own time, according to the laws of physics, without haste, without concern for observers. We, with our short lives and quick thoughts, are just brief witnesses to these long, slow processes. A comet passing by is a chance to touch that deep time, to see something that connects us to the distant past and the distant future. It's a humbling and comforting thought. We're part of something much larger and older than ourselves. Tonight, you don't need to chase thoughts about comets or orbits or physics. Let them pass like distant comets themselves, bright for a moment, interesting and beautiful, and then gone. You don't need to hold on to any of this. The knowledge is there if you want it, but right now you can just rest. The comets will continue their journeys whether you think about them or not. The universe will keep unfolding its slow stories. The stars will keep shining, the earth will keep turning, and you can let all of that be, without needing to understand it, without needing to remember it. Just breathe slowly. Feel the weight of your body against the surface beneath you. Notice the quiet. Notice the stillness. You're safe here. You're part of the same universe as the comets, made of the same atoms, following the same laws, and right now your only task is to rest. As you breathe slowly, you can rest inside the same gentle rhythm that guides comets through space. It's steady, quiet, and always moving forward, but there's no urgency. Each breath is like a small orbit, a cycle that completes and begins again. In and out, rise and fall, movement and stillness. The comet doesn't worry about its path. It doesn't wonder if it's going the right way. It simply moves, pulled by gravity, shaped by the physics of the universe, patient and persistent. You can be like that too. You don't need to plan or solve or remember. You can just be, just breathe, just rest. The next breath will come on its own. The next thought will pass on its own. Everything will continue in its own rhythm, and you can trust that. You can let go. Just one more small breath, slow and easy, and then we drift. The comets are out there, moving through the cold and the dark, silent and patient. Some are approaching the sun, warming and brightening. Some are retreating, cooling and fading. Some are far away, barely moving at all against the backdrop of stars. They'll all keep going, each on its own path, each following its own time, and you can rest here, knowing that everything is where it needs to be, including you. The universe is vast, and it's been here for billions of years, and it will be here for billions more. Tonight, In this small moment, you can simply rest within it. You're safe. You're held by the same gravity that guides planets and comets. You're part of the same story, the same slow unfolding. And right now, the only thing you need to do is breathe and rest and drift. Just one more small breath, and then we drift. The next story is about to begin. Please relax and enjoy. The night sky holds a gentle secret that appears most often near the poles of our planet. If you were standing in the dark expanse of northern Alaska on a clear winter evening, or perhaps on the windswept coast of Norway, you might look up and see something that seems almost impossible. Curtains of light flowing across the darkness, glowing in shades of green and sometimes red or purple, moving slowly like fabric caught in an invisible breeze. These are auroras, natural light displays that happen in Earth's upper atmosphere, and they are among the most beautiful phenomena our planet has to offer. The lights you would see in the north are called aurora borealis, a name that comes from Aurora, the Roman goddess of dawn, and Boreas, the Greek god of the north wind. In the southern hemisphere, the same phenomenon occurs and is called aurora australis, with australis simply meaning southern. Both are the same kind of event, just happening at opposite ends of the Earth, and both are part of a quiet, ongoing conversation between our planet and the sun. To understand what an aurora truly is, we need to think about what happens high above us, far beyond where airplanes fly, far beyond where weather occurs, in a region of the atmosphere so high and so thin that most people never think about it at all. Auroras happen when energetic particles from space enter the region near Earth's poles and interact with the gases in our upper atmosphere. Most of those particles come from the sun, travelling across the vast emptiness of space for days before they arrive at Earth. When they get here, Earth's magnetic field, an invisible shield that surrounds our planet, guides these particles toward the polar regions, funneling them downward along curved pathways that dip toward the surface near the Arctic and Antarctic. The light you see during an aurora appears when these fast-moving particles collide with atmospheric gases like oxygen and nitrogen. Those collisions excite the atoms and molecules, which is a way of saying the particles transfer some of their energy to the gases, like gently charging them up. When the gases relax back down to their normal state, they release that extra energy as light, and that light is what we see as an aurora. It's a process that happens continuously, high above the clouds, invisible during the day, but revealed in all its quiet beauty when the sun sets and darkness falls. Auroras are most common in a ring-shaped zone around each pole called the auroral oval. This oval isn't a perfect circle, and it doesn't sit exactly at the geographic pole. Instead, it's centered around the magnetic pole, which is offset from the true north and south poles by several degrees. The auroral oval shifts and changes size depending on how active the sun is and how much energy is flowing into Earth's magnetosphere. But on average, it forms a band that passes over places like northern Scandinavia, Iceland, Alaska, northern Canada and Siberia in the north, and over Antarctica, and occasionally the southern tips of New Zealand and Tasmania in the south. If you live within or near this oval, you have a much better chance of seeing auroras on any given night. If you live farther away, toward the equator, auroras are rare, though during particularly strong geomagnetic storms, the oval can expand and push the lights farther south or north than usual, sometimes bringing them within view of places that almost never see them. Auroras are easier to see at high latitudes, which simply means the farther north or south you go, the more likely you are to witness them. In the northern hemisphere, they often appear in Alaska, northern Canada, Iceland, Norway, Sweden and Finland. These regions fall within or close to the auroral oval, and during periods of higher solar activity, auroras can be a regular sight, appearing several times a week or even multiple times in a single night. In the southern hemisphere, the situation is a bit different, because there's less populated land at high latitudes. Antarctica is the prime location, but because few people live there, most southern aurora sightings come from places like southern New Zealand, Tasmania, and occasionally the southern tips of South America and South Africa during strong auroral events. The southern lights are just as beautiful as the northern ones, but they're seen by far fewer people simply because there are fewer people living in those remote areas. One thing that surprises many people is that auroras don't happen at ground level. They're not like fog or clouds that you can walk through or touch. Auroras glow high above the surface, suspended in the upper atmosphere like a luminous painting that hangs in the sky. The typical altitude where auroras begin to appear is around 80 to 100 kilometers up. To put that in perspective, commercial airplanes fly at about 10 to 12 kilometers, and even the highest clouds, the wispy cirrus clouds, only reach about 10 to 15 kilometers. Auroras start much higher, well into the region called the thermosphere, where the air is so thin that it would feel like a near vacuum if you could somehow be transported there. Some auroras can reach even higher, extending up to several hundred kilometers above the surface. The exact altitude depends on the energy of the incoming particles and the type of gas they're colliding with. But the point is that auroras are a high-altitude phenomenon, something that happens in a part of the atmosphere most of us never interact with in our daily lives. The reason auroras are concentrated near the poles has to do with Earth's magnetic field. The magnetic field is generated deep inside the planet by the motion of molten iron in the outer core, and it extends far out into space, creating a protective bubble around Earth called the magnetosphere. The field lines of this magnetic field loop out from the southern hemisphere, arc through space, and come back down in the northern hemisphere. Near the equator, these field lines are nearly horizontal, running parallel to the surface, but near the poles, they dip steeply downward, pointing almost straight into the Earth. These downward-pointing field lines act like invisible pathways for charged particles. When particles from the Sun encounter Earth's magnetosphere, they get caught up in the magnetic field and are guided along these field lines. Because the field lines converge near the poles, the particles are funneled downward into the upper atmosphere in those regions, where they collide with gases and create the glowing displays we call auroras. The poles are special not because they're colder or darker, but because the geometry of Earth's magnetic field naturally directs energetic particles there. The auroral oval itself is not a fixed ring. It expands and contracts depending on how much energy is being delivered to Earth's magnetosphere by the solar wind. During periods of low solar activity, the oval is smaller and sits closer to the magnetic poles. During stronger solar activity, when more particles are streaming toward Earth, or when a particularly energetic burst of solar material arrives, the oval expands, sometimes dramatically. This is why, during big geomagnetic storms, auroras can be seen much farther from the poles than usual. People in places like Scotland, northern parts of the United States, or even farther south have occasionally witnessed auroras during these intense events. The expansion of the auroral oval is a direct response to increased energy input from the Sun, and it's one of the ways scientists can tell when a geomagnetic storm is underway. Now, let's talk about the colours, because the colours of an aurora are one of the most striking things about them, and they're also a direct result of the physics happening in the upper atmosphere. Green is by far the most common aurora colour. If you were to look at 100 different auroras, the vast majority would feature green as their dominant hue. This green light often comes from excited oxygen atoms. When a fast-moving particle from the Sun collides with an oxygen atom in the thermosphere, it can knock one of the atom's electrons into a higher energy level. The electron doesn't stay there for long, it quickly falls back down to its normal state, and when it does, it releases the extra energy as a photon of light. For oxygen atoms at certain altitudes, that photon happens to be green, with a wavelength around 557.7 nanometers, which is right in the middle of the visible spectrum and very close to the wavelength our eyes are most sensitive to. Green auroras frequently glow at altitudes around 100 to 150 kilometers, where the atmospheric density is just right for this process to dominate. Red auroras are also caused by oxygen, but they tend to appear at higher altitudes, usually above 200 kilometers, at these greater heights. The air is even thinner, and the collisions between particles and oxygen atoms happen less frequently. This gives the oxygen atoms more time to relax from their excited state, and under these conditions they emit red light instead of green. Red auroras are less common than green ones, partly because they require specific conditions and partly because they're often fainter and harder to see. When they do appear, they can add a stunning layer to the display, sometimes forming a red glow above the green curtains, creating a layered effect that looks almost like a watercolour painting spread across the sky. Blue and purple tones in auroras often involve nitrogen. Nitrogen makes up about 78% of Earth's atmosphere, so it's abundant even at high altitudes, and when charged particles collide with nitrogen molecules, they can produce blue and purple light. Lower altitude auroras, those happening closer to 80 or 90 kilometers up, tend to show more purples and blues because that's where nitrogen is relatively more dense. The exact shade depends on whether the nitrogen is in its molecular form or has been broken apart into individual atoms, and on how much energy the incoming particles are carrying. Sometimes you'll see a mix of blue at the bottom edge of an aurora with green higher up and red higher still, creating a spectrum of colours that reflects the changing composition and density of the atmosphere with altitude. The colour of an aurora depends on two main things: which gas is glowing and at what altitude the collisions are occurring. It also depends on how much energy the incoming particles carry. Higher energy particles can penetrate deeper into the atmosphere before they lose their energy through collisions, so they tend to create lower altitude auroras with more blues and purples. Lower energy particles are stopped higher up, where they produce greens and reds from oxygen. Many auroras are a blend of colours layered by altitude, like soft curtains hanging in the sky. From the ground you might see green at the base, fading to red at the top, with hints of purple or blue at the edges. It's a natural spectrum created by the chemistry and physics of the atmosphere, and it changes moment by moment as conditions shift. Auroras don't just appear as shapeless blobs of light, they take on distinct forms and structures that can change over the course of a display, sometimes slowly, sometimes quickly. Many auroras begin as calm arcs across the sky, smooth bands of light that stretch from one side of the horizon to the other, often running roughly east to west. These arcs can be quite faint at first, barely visible, like a faint glow just above the northern or southern horizon. As the aurora strengthens, the arc might brighten and begin to develop structure. It can form tall curtains that ripple and fold like fabric hanging in the air. These curtains can wave gently, their lower edges sharp and their tops fading into darkness, and they can extend vertically for hundreds of kilometers, though they always remain high above the ground. Some auroras appear as bands that stretch from horizon to horizon, and within those bands you might see fine vertical stripes called rays. These rays align with Earth's magnetic field lines, and they give the aurora a striated appearance, like columns of light extending upward. The rays can be quite narrow, just a few hundred meters across, and they can move and shift as the magnetic field and particle flows change. When an aurora is directly overhead, it can form a shape called a corona, where the rays seem to spread outward from a central point, like the spokes of a wheel or the petals of a flower. This is actually an optical effect caused by perspective. The rays are still aligned with the magnetic field, but because you're looking up at them from below, they appear to radiate outward. It's one of the most dramatic forms an aurora can take, and it's a sign that you're standing right under the auroral oval. The motion of auroras is one of their most mesmerizing qualities. They're not static. They brighten and dim in pulses, they drift across the sky, they ripple and wave. This motion comes from changes in the flow of particles and the conditions in the magnetosphere. Sometimes the aurora moves slowly, drifting gently from one part of the sky to another, over the course of minutes or hours. Other times it can dance quickly, with curtains flaring up, brightening, and then fading in just seconds. The speed of the motion doesn't mean the light itself is moving that fast. Remember, the glow is happening far above the clouds, and what you're seeing is the result of changing conditions in the upper atmosphere and magnetosphere. It's like watching a spotlight play across a distant surface. The light itself doesn't move, but the pattern it creates does. Even when auroras look like they're moving fast, it's important to remember that the glow is still, happening far above us. The curtains and arcs are not rushing through the air like a storm. They're the result of regions of the upper atmosphere being excited by incoming particles, and as those regions shift and change, the glow shifts with them. It's a dynamic process, constantly responding to variations in the solar wind and the magnetosphere, and that's what gives auroras their living, breathing quality. They can brighten and dim in pulses, almost like they're breathing, and they can develop sudden bright patches called auroral substorms, where a relatively calm aurora suddenly erupts into a brighter, more active display. These substorms are caused by the release of energy that is built up in Earth's magnetotail, and they can make the aurora much more dramatic for a short period, usually lasting from a few minutes to an hour or so. To really understand auroras, we need to talk about the sun's role, because without the sun there would be no auroras on Earth. The sun is not a static ball of light in the sky. It's an incredibly active, dynamic star, constantly churning and roiling with nuclear reactions in its core and complex magnetic activity in its outer layers. The Sun continuously releases a stream of particles called the solar wind. This wind is made up mostly of electrons and protons, and it flows outward from the Sun in all directions, filling the solar system. The solar wind carries with it the Sun's magnetic field, stretching it out into space like a web that permeates the entire region around the Sun. The speed of the solar wind varies, but it typically travels at about 400 kilometers per second, though it can be faster or slower depending on conditions on the Sun. Auroras get stronger when solar wind conditions are more intense. If the solar wind is blowing harder, carrying more particles and more energy, then more of those particles can interact with Earth's magnetosphere, and more energy can be transferred into the upper atmosphere, creating brighter and more active auroras. But the solar wind is not the only factor. Sometimes the Sun releases sudden, dramatic bursts of material and energy. One of these is called a coronal mass ejection, or CME. A CME is an enormous eruption of plasma and magnetic field from the Sun's corona, the outermost part of its atmosphere. When a CME is directed toward Earth, it can send billions of tons of solar material hurtling through space toward us. When this material arrives, usually 1 to 3 days after the eruption, it can trigger a geomagnetic storm, compressing Earth's magnetosphere and injecting large amounts of energy into it. This can cause the auroral oval to expand dramatically, bringing auroras to latitudes much farther from the poles than usual, and making the displays much brighter and more active. Solar flares are another type of solar activity that can affect auroras. A solar flare is a sudden, intense burst of energy from the Sun's surface caused by the rearrangement of magnetic fields in the Sun's atmosphere. Flares release energy across the electromagnetic spectrum, from radio waves to X-rays, and they can also accelerate particles to very high speeds. If the flare is associated with a CME, the combined effect can be particularly strong. Not all flares lead to enhanced auroras, though. It depends on whether the particles and energy are directed toward Earth, and whether the magnetic fields in the solar wind align in a way that allows them to couple efficiently with Earth's magnetosphere. Coronal holes are another feature of the Sun that can influence auroras. A coronal hole is a region of the Sun's atmosphere where the magnetic field is open, allowing solar wind to escape more easily. These regions appear dark in certain wavelengths of light, because they're cooler and less dense than the surrounding areas. When a coronal hole is facing Earth, the fast solar winds streaming from it can enhance aurora activity when it reaches our planet. These high-speed streams are more persistent than CMEs, often lasting for several days as the Sun rotates and the coronal hole sweeps past Earth like a cosmic lighthouse beam. All of this solar activity, the solar wind, CMEs, flares and coronal holes, is part of the Sun's normal behaviour. The Sun goes through cycles of activity, with periods of higher and lower activity following a roughly 11-year pattern called the solar cycle. During solar maximum, when the Sun is most active, there are more sunspots, more flares, more CMEs, and generally more auroras on Earth. During solar minimum, activity is lower, and auroras are less frequent and less intense, though they still occur. Space weather is the term scientists use to describe these changing conditions in the solar wind and the near-Earth environment, and just like weather on the ground, it's always changing. But unlike terrestrial weather, space weather is driven by events happening 93 million miles away on the Sun, and it affects the invisible magnetic and particle environment around our planet rather than the air we breathe. You can think of auroras as Earth's gentle response to the Sun's outgoing flow. The Sun is constantly shedding material and energy, and when that material reaches Earth, our planet's magnetic field responds by guiding some of it toward the poles and converting it into light. It's a process that's been happening for as long as Earth has had a magnetic field and an atmosphere, which is to say for billions of years. The aurora you see on any given night is part of a continuous conversation between our planet and its star, a reminder that we live in a solar system, not in isolation, and that the space between Earth and the Sun is not empty, but filled with particles and fields and activity. Earth's magnetic field plays a crucial role in creating auroras, and to understand how, we need to think about the structure of this field and how it interacts with the solar wind. The magnetic bubble that surrounds Earth is called the magnetosphere. It's not a physical structure. It's a region where Earth's magnetic field is strong enough to dominate the behavior of charged particles. The magnetosphere extends tens of thousands of kilometers into space, and it acts as a shield, deflecting many of the charged particles from the solar wind away from Earth. Without it, those particles would stream directly toward the surface, where they could damage the atmosphere and potentially harm life. The magnetosphere is constantly being buffeted and shaped by the solar wind, which is why it doesn't have a simple, symmetrical shape. On the side of Earth facing the Sun, the magnetosphere is compressed by the pressure of the solar wind. The boundary between the magnetosphere and the solar wind, called the magnetopause, can be pushed inward to within about 10 Earth radii on the day side. On the night side of Earth, away from the Sun, the magnetosphere is stretched out into a long tail called the magnetotail. This tail can extend for millions of kilometers downstream, far beyond the Moon's orbit. The magnetotail is not just an empty extension of the magnetic field. It's a region where energy can build up, stored in the stretched and stressed magnetic field lines. When conditions are right, this energy can be released suddenly in a process related to magnetic reconnection. Magnetic reconnection is a fundamental process in plasma physics, and it plays a key role in creating auroras. It happens when magnetic field lines that are pointing in opposite directions come close together and suddenly snap and reconnect in a new configuration. When this happens, it releases a large amount of stored magnetic energy very quickly, and that energy can go into accelerating charged particles to high speeds. In the magnetotail, reconnection can cause field lines to snap back toward Earth, flinging particles earthward along the field lines. Those particles then follow the field lines down into the upper atmosphere near the poles, where they collide with gases and create auroras. This is why auroras can suddenly brighten or become more active. It's often a sign that a reconnection event has occurred in the magnetotail, releasing energy and sending a fresh batch of particles streaming toward the atmosphere. Auroras are, in a sense, one visible sign that the magnetosphere is active and protective. The same processes that create the beautiful lights in the sky are also processes that prevent harmful radiation and particles from reaching the surface. The magnetosphere is constantly interacting with the solar wind, absorbing energy, deflecting particles, and occasionally releasing that energy in bursts that light up the polar skies. It's a dynamic, ever-changing system, and auroras are just one of the many ways we can observe its activity from the ground. One common question people have about auroras is why we typically see them at night. The answer is simple. Auroras actually occur during the daytime as well, but sunlight makes them impossible to see. The glow of an aurora, even a bright one, is faint compared to the scattered sunlight that fills the sky during the day. When the sun is up, the entire sky is illuminated, and the relatively dim glow of the aurora is completely washed out. It's only when the sun sets and darkness falls that your eyes can pick up the faint light of the aurora against the dark background of the night sky. Darkness helps your eyes become more sensitive, and it reveals the subtle glows and colours that would otherwise be invisible. Clear skies are essential for seeing auroras. Clouds block your view of the upper atmosphere just as they block your view of stars and planets. If there's a thick layer of clouds between you and the aurora, you won't see it, no matter how bright it is. This is why aurora watchers always check the weather forecast, hoping for clear conditions. Low light pollution also makes a big difference. In a city with bright streetlights and buildings, the sky glow can make it hard to see faint auroras. Out in the countryside, far from artificial lights, even a relatively weak aurora can be quite visible. The contrast between the dark sky and the glowing aurora is much greater when there's no competing light pollution. Auroras can be dim and still beautiful. Not every aurora is a bright, dramatic display that fills the sky with vivid colours. Some are faint and subtle, like a pale watercolour wash across the northern or southern horizon. These faint auroras are still the same phenomenon. They're just the result of less energetic conditions in the magnetosphere. Even a dim aurora is worth watching though, because it can change. A faint arc can suddenly brighten, or it can develop structure, or it can slowly fade away. There's a quiet beauty in watching the sky and seeing these subtle changes unfold. The brightness of the moon can also affect aurora visibility. A full moon is bright enough to illuminate the landscape and create a significant amount of sky glow, which can reduce the visibility of faint auroras. Many aurora photographers prefer nights with little or no moonlight because it allows the aurora to stand out more clearly. However, a bright moon can also be helpful because it illuminates the foreground, allowing you to see the landscape as well as the aurora, which can make for beautiful photographs with both the aurora and the surrounding environment visible. Winter often provides the best aurora watching conditions, especially at high latitudes, and the reason is straightforward. Nights are longer. In the Arctic and Antarctic during winter, the night can last for many hours, or in some places near the poles for weeks or even months. This extended darkness gives you more time to observe auroras and increases the chances that you'll be looking at the sky when an aurora appears. Summer, on the other hand, can have very short nights or none at all in the far north or south, making aurora viewing difficult or impossible simply because it never gets dark enough. The aurora is still happening, but you can't see it against the bright twilight sky. Auroras are frequently seen around local midnight, but they can appear at any time during the night. The exact timing depends on many factors, including your location relative to the auroral oval, the level of geomagnetic activity, and the configuration of the magnetosphere. Sometimes auroras appear shortly after sunset, sometimes in the early morning hours before dawn, and sometimes they're visible all night long during particularly active periods. The auroral oval itself shifts over the course of the night as Earth rotates, so the best spot to see an aurora can change from hour to hour. This is why patience is an important part of aurora watching. Sometimes the sky is quiet for hours, and then slowly, almost imperceptibly, a faint glow begins to appear on the horizon, and over the next minutes or hours it grows and develops into a full display. Other times the sky remains dark all night. Aurora watching requires a willingness to wait, to watch, and to accept that nature operates on its own schedule. There are some calm curiosities about auroras that are worth mentioning. One is the question of sound. Auroras are usually silent to most observers. They're happening so high up in the atmosphere, in such thin air, that there's no mechanism for sound to be generated in the way we normally think of it. However, some people, particularly indigenous peoples in the Arctic, and a small number of scientists and aurora watchers, have reported hearing faint sounds during auroras. These sounds are described as crackling, swishing, or rustling noises, and they're very uncommon. The exact cause is still debated. One theory is that the sounds are related to electromagnetic effects during very strong auroras, perhaps causing discharges or vibrations in objects near the observer, but this remains uncertain. For the vast majority of people, auroras are a purely visual experience, silent and serene. Cameras often capture aurora colours more strongly than the naked eye. This is because camera sensors, especially those with long exposure capabilities, can accumulate light over several seconds, making faint glows much brighter and bringing out colours that your eyes might perceive as white or pale green. Your eyes are not as sensitive to colour in low light conditions. In dim environments, your vision relies more on rod cells, which are good at detecting light but not colour, while cone cells, which detect colour, are less effective. This is why a faint aurora might look greyish or pale greenish to your eyes, but appear vividly green or even red in a photograph. Long exposure photos can reveal detail and structure that you might miss with the naked eye, showing fine rays, colour gradations, and subtle movements frozen in time. This doesn't mean the camera is lying. It's just capturing light in a different way than your eyes do, integrating more photons over time and revealing what's really there. Auroras are not reflections of city lights on clouds, though this is a common misconception. They're also not caused by cold air itself, even though they're often seen in cold climates. The cold is incidental. It's just that high latitudes, where auroras are common, also happen to be cold, especially in winter. The aurora is caused by particles from space interacting with the atmosphere, not by temperature. Auroras are also not the same as meteor showers, which are caused by small pieces of rock and dust burning up as they enter the atmosphere. Meteors are brief streaks of light that last only a second or two, while auroras are glows that can persist for hours and have distinct shapes and structures. Auroras can appear above clouds, which is why mountains and high elevations can sometimes help with viewing. If you're standing on a mountaintop and there are low clouds in the valleys below, you might still see an aurora in the sky above you because the aurora is happening far higher than the clouds. Clouds are typically below 10 or 15 kilometers, while auroras start at 80 kilometers or higher, so there's no overlap. However, if there are clouds directly overhead, they'll block your view just as they would from lower elevations. Auroras can look different from minute to minute, and two people watching the same aurora can notice different colours or details based on their eyesight, the sensitivity of their eyes, and, if they're taking photos, their camera settings. Some people are more sensitive to green light, others to red. Some cameras are more sensitive to certain wavelengths. This means that your experience of an aurora is somewhat subjective, shaped by your own eyes and perception, and that's part of what makes it personal and special. Auroras are not unique to Earth. They happen on other planets in our solar system, as well wherever there's a magnetic field and an atmosphere, or at least some source of particles. Jupiter, for instance, has powerful auroras that are even more dramatic than Earth's. Jupiter's auroras are driven both by the solar wind and by material from its volcanic moon Io, which constantly spews charged particles into space. Those particles get caught in Jupiter's enormous magnetic field, which is much stronger than Earth's, and they're funneled down to the planet's poles, creating auroras that are visible in ultraviolet and infrared wavelengths. Observations from spacecraft like the Hubble Space Telescope and the Juno mission have shown that Jupiter's auroras are constantly active and incredibly bright. Saturn also has auroras, often seen in ultraviolet light by spacecraft instruments. Saturn's auroras are similar to Earth's in some ways, driven by the solar wind interacting with Saturn's magnetic field, but they also have unique features related to Saturn's magnetosphere and its interactions with its rings and moons. Even Mars, which has a much weaker global magnetic field than Earth, can show aurora-like glows. Mars lost most of its global magnetic field billions of years ago, but it still has patches of magnetized crust in certain regions, and when solar wind particles interact with those regions, they can create localized auroral glows. Mars's auroras are different from Earth's because they're not confined to polar regions. They can appear wherever there's a strong enough local magnetic field. Studying auroras on other planets teaches scientists about how atmospheres and magnetic fields interact in different environments. It's a way of testing our understanding of the physics that creates auroras and seeing how those principles apply in places with different magnetic field strengths, atmospheric compositions, and solar wind conditions. Auroras are linked to the same physics behind many plasma phenomena in space, from solar flares to the interactions of stellar winds with exoplanets orbiting distant stars. Understanding auroras on Earth and other planets helps us understand the broader behavior of magnetized plasmas throughout the universe. The connection between the Sun and Earth is ongoing, even when we can't see it. The solar wind is always blowing, Earth's magnetosphere is always responding, and particles are always being guided toward the poles. The fact that we can't see auroras during the day or from lower latitudes doesn't mean they're not happening. The auroral oval can be tracked and forecasted using space weather data. Satellites monitor the Sun, watching for CMEs and solar flares, and they also monitor the solar wind as it flows past Earth, measuring its speed, density, and magnetic field orientation. This data allows scientists to predict when conditions are favourable for auroras and to issue forecasts and alerts for aurora watchers. These forecasts aren't perfect. Space weather is complex and difficult to predict with high precision, but they're useful for giving people an idea of when to look up. Aurora activity rises and falls with the Sun's roughly 11-year solar cycle. During solar maximum, when the Sun is at its most active, there are more opportunities for strong auroras, and the auroral oval expands more frequently, bringing auroras to lower latitudes. During solar minimum, when the Sun is quieter, auroras are less frequent and generally confined to higher latitudes. This doesn't mean there are no auroras during solar minimum. There are still quiet, steady streams of solar wind, and there can still be occasional CMEs or high-speed streams from coronal holes, any of which can produce auroras. But on average, you'll see more auroras and more intense ones during the active years of the solar cycle. Over long-time scales, auroras are part of Earth's continuing relationship with its star. They've been happening for as long as Earth has had a magnetic field and an atmosphere, which is billions of years. Ancient people saw them and created myths and legends to explain them. Some cultures thought they were spirits, others saw them as omens or messages from the gods. In some indigenous Arctic cultures, auroras were believed to be the souls of ancestors dancing in the sky. In Norse mythology, they were thought to be reflections from the shields of the Valkyries. These stories reflect the human need to understand and find meaning in natural phenomena, and they remind us that auroras have inspired awe and wonder for as long as humans have looked up at the night sky. Today, we understand the science behind auroras, and that understanding doesn't diminish their beauty. If anything, it enhances it. knowing that you're watching energetic particles from the sun colliding with oxygen and nitrogen atoms 100 kilometers above your head, guided there by invisible magnetic field lines, makes the experience even more remarkable. You're seeing a direct connection between Earth and the sun, a visible manifestation of the solar wind and the magnetosphere, a process that's been unfolding for eons and will continue long into the future. Even in a quiet room, far from any aurora, Earth is moving through the solar wind. Right now, as you read this or listen to this, the solar wind is streaming past Earth. Particles are interacting with the magnetosphere, and somewhere on the planet, if conditions are right, the upper atmosphere may be softly glowing. You don't have to see it to know it's happening. Earth's magnetic field is quietly steering charged particles away from you, protecting the surface, and occasionally those particles create the gentle light shows we call auroras. It's a process that requires nothing from you, no action, no intervention. It simply happens, a natural consequence of living on a magnetized planet orbiting an active star. Auroras remind us that space is not some distant, unreachable frontier. It's right here, brushing against the edges of our atmosphere, interacting with our planet in ways both visible and invisible. The same oxygen you breathe, the oxygen that makes up about 21% of the air, can glow high above as green light when struck by particles from the sun. The same nitrogen that makes up 78% of the air can contribute blue and purple shades to an aurora. These are the same gases, just behaving differently because they are in a different environment, high and thin and energized. The dancing motion of an aurora, the way it ripples and waves and brightens and fades, is energy becoming light, and then fading back into calm. The particles collide, the atoms get excited, the energy is released as photons, and then everything settles back down, only to be excited again moments later. It's a cycle, a flow, a continuous transformation of energy from one form to another. There's something deeply soothing about that, about watching a process that's entirely natural and beyond your control, something that happens whether you're there to see it or not. Nothing about an aurora needs you to do anything. Its beauty is effortless. It doesn't ask for your attention or your approval. It simply is. You can watch it or not, photograph it or not, understand it or not, and it will continue to glow high above, following the laws of physics and the whims of the solar wind. This is true of so many natural phenomena, but auroras make it particularly clear because they're so visible and so dramatic when they occur, yet so independent of human activity. You can let your thoughts behave like aurora curtains. Let them rise, shimmer, shift, and drift away. Thoughts don't need to be held tightly or controlled any more than an aurora needs to be controlled. They can appear, glow for a while, change shape, and fade, and that's perfectly fine. There's a kind of gentle permission in that idea, a reminder that not everything needs to be managed or understood or fixed. Some things can just be observed, appreciated for what they are, and then allowed to move on. As you breathe slowly, in and out, you can rest knowing that somewhere, right now, the sky keeps its quiet glow. It might be over Alaska or Norway or Antarctica or somewhere else in the auroral oval. It might be bright and vivid, or it might be faint and subtle. Either way, it's there, steady and harmless and patient, a reminder of the ongoing connection between Earth and Sun, a visible sign of invisible processes, a light in the darkness that asks nothing of you and offers everything. The particles continue to stream from the Sun. The magnetosphere continues to guide them toward the poles. The atmospheric gases continue to glow when struck. And you, wherever you are, can close your eyes and know that this process is unfolding, has been unfolding for billions of years, and will continue long after you're asleep. The aurora doesn't need you to witness it to be real, and you don't need to do anything for it to happen. It's a gift of nature, a byproduct of the physics of our solar system, a gentle reminder that the universe is full of beauty that simply exists, whether we see it or not. The aurora will be there tomorrow night, and the night after that, and for countless nights to come, a constant, gentle presence in the polar skies, waiting for anyone who cares to look up. And when you do look up, when you stand beneath an aurora for the first time, there's often a moment of disbelief, a sense that what you're seeing can't quite be real. The lights move in ways that seem almost liquid, almost alive, and yet they're silent and distant and completely indifferent to your presence. This combination of movement and silence creates a strange dreamlike quality that many people find difficult to describe, It's not like watching a sunset which follows a predictable arc across the sky. It's not like watching stars which are fixed points of light. An aurora is dynamic but slow, energetic but gentle, brilliant but ephemeral. It exists in a category of its own, a phenomenon that doesn't quite fit with anything else in our everyday experience of the natural world. The science behind auroras is well understood now, worked out over decades of careful observation and theoretical development, but that understanding came gradually. For most of human history, auroras were mysterious. Ancient observers could see that something was happening in the sky, but they had no way to know what or why. The lights appeared without warning, moved in unpredictable ways, and disappeared just as mysteriously. Different cultures developed different explanations based on their own worldviews and mythologies. In medieval Europe, auroras were sometimes interpreted as signs of war or disaster, blood in the sky foretelling conflict. In China, they were occasionally recorded in historical texts as unusual atmospheric phenomena, though they were rare at those latitudes. In the Arctic, indigenous peoples lived with auroras as a regular part of their environment and developed rich traditions around them, some seeing them as playful spirits, others as dangerous forces to be respected. It wasn't until the scientific revolution that people began to approach auroras with the tools of systematic observation and experimentation. In the 18th century, scientists started to notice patterns. Auroras seemed to be more common at certain latitudes. They seemed to vary in frequency over time, becoming more common during some years and less common during others. Careful observers noted that auroras often appeared to align roughly north-south, following what we now know are magnetic field lines. But the mechanism remained a mystery. How could light appear in the sky without any apparent source? What was making the air glow? The breakthrough came in stages. In the 19th century, scientists discovered that Earth has a magnetic field, and they began to map its shape and strength. They also discovered that the sun was not a static object but showed features like sunspots that varied over time. Some observers noticed a correlation between sunspot activity and the frequency of auroras, suggesting a connection between the sun and these atmospheric lights. But the nature of that connection remained unclear. What was travelling from the sun to Earth? How was it causing the atmosphere to glow? The answer required understanding that the sun emits more than just light. In the early 20th century, scientists proposed that the sun releases streams of charged particles, and in the 1950s and 1960s, this solar wind was finally detected and measured by spacecraft. Around the same time, scientists worked out the details of how charged particles interact with magnetic fields and how they can be guided along field lines. They developed the theory of the magnetosphere, understanding that Earth's magnetic field creates a protective bubble that shapes the flow of the solar wind around the planet. They figured out that particles can be trapped in the magnetosphere, bouncing back and forth along field lines, and that under certain conditions they can be accelerated downward into the atmosphere where they collide with gases and produce light. This understanding brought together physics from many different domains: electromagnetism, plasma physics, atomic physics, atmospheric science. Auroras turned out to be a window into processes happening throughout the solar system and beyond. They became a subject of serious scientific study, with dedicated research programs, satellite missions, and ground-based observatories all working to understand the details. Today, we have a comprehensive picture of how auroras work, though there are still details being refined and new discoveries being made. Science is never truly finished. It's always finding new layers of complexity and new questions to ask. One of the interesting things about auroras is that they're both local and global. They're local in the sense that they happen in specific places, the auroral ovals around the poles, and if you're not in those places, you won't see them. But they're global in the sense that they're the result of processes that affect the entire magnetosphere, the entire relationship between Earth and the Sun. When a coronal mass ejection leaves the Sun, it affects the entire dayside magnetosphere when it arrives. The compression and energy input ripple through the system, affecting the magnetotail, the particle populations trapped in various regions, and the coupling between the magnetosphere and the ionosphere. The aurora you see in Alaska is connected to processes happening on the other side of the planet, in the magnetotail stretching millions of kilometers into space, and to events that occurred on the Sun days earlier. It's all one interconnected system. The ionosphere is another important player in the aurora story. The ionosphere is the part of the upper atmosphere, where there are enough free electrons and ions to affect the propagation of radio waves. It overlaps with the region where auroras occur, roughly from about 60 to 1,000 kilometers altitude. During an aurora, the incoming particles increase the ionization in the ionosphere, creating more free electrons and ions. This can affect radio communications and GPS signals, sometimes causing disruptions or errors. This is one reason why understanding and forecasting auroras is not just a matter of scientific curiosity, it has practical applications. Airlines flying polar routes need to know about space weather conditions because increased radiation during geomagnetic storms can pose risks to passengers and crew at high altitudes. Satellite operators need to know because increased drag from the swollen upper atmosphere during storms can affect satellite orbits. Power grid operators need to know because geomagnetic storms can induce currents in long power lines, potentially damaging transformers. The connection between auroras and technology is a reminder that we live in a technological civilization that depends on infrastructure extending into space and operating in the upper atmosphere. That infrastructure is affected by space weather, and auroras are one visible sign of space weather in action. The same geomagnetic storm that creates beautiful auroras can also create problems for GPS, communications, and power grids. It's a dual nature, beautiful and potentially disruptive, a natural phenomenon that we admire and also have to manage. But most of the time, auroras are simply beautiful and harmless. For every geomagnetic storm that causes technological issues, there are dozens or hundreds of quiet auroral displays that do nothing but light up the polar skies. These quieter auroras are the result of the steady background solar wind interacting with the magnetosphere in a more gentle way. They're less dramatic than the big displays during storms, but they're more common, and they're just as real, just as much a part of the ongoing Sun-Earth connection. Watching an aurora can be a meditative experience. There's a stillness required, a willingness to stand outside in the cold, often for hours, just watching the sky. Many aurora watchers describe a sense of peace that comes from this. You're not in control of whether the aurora appears or how bright it is or how long it lasts. You're simply there, a witness, watching something unfold according to its own logic. This kind of patient observation is increasingly rare in modern life, where so much is instant and controllable. An aurora can't be summoned or paused or replayed. It happens in real time, and if you miss it, it's gone. This ephemerality is part of its charm. Photographers have a different relationship with auroras. For them, the aurora is both a subject and a challenge. Capturing an aurora well requires technical skill, knowing how to set a camera for long exposures, how to focus in the dark, how to balance the brightness of the aurora with the darkness of the sky, how to include interesting foreground elements without letting them become silhouettes. Many aurora photographers spend years refining their technique, learning the best settings for different conditions, scouting locations during the day so they know where to set up at night. The results can be stunning, images that reveal details and colours that are barely visible to the naked eye. But even the best photograph is just a representation, a frozen moment extracted from a dynamic flowing display. The real aurora is always richer, always more complex than any single image can capture. There's also a social aspect to aurora watching. In places where auroras are common, communities develop around them. People share forecasts and sightings, they gather in favourite viewing spots, they exchange tips about where to go and when. Online communities have formed where aurora watchers from around the world post photos, discuss conditions and share their excitement. For some people, chasing auroras becomes a passion, even an obsession. They travel to remote locations, they plan trips around solar activity forecasts, they stay up all night in freezing temperatures just for the chance to see a particularly good display. This dedication might seem extreme to outsiders, but for those involved, it's entirely logical. Auroras are worth the effort, worth the discomfort, worth the time and expense because they offer something that few other experiences can match: a direct, visible connection to the cosmos, a reminder of our place in a vast and dynamic universe. For scientists, auroras are not just beautiful, they're data. Every aurora is a measurement, a record of conditions in the magnetosphere and the solar wind. Ground-based instruments measure the aurora's brightness and colour. Radar systems track the motions of particles in the ionosphere. Magnetometers measure disturbances in Earth's magnetic field. And all of this data goes into building a more complete picture of how the Sun-Earth system works. Satellites in orbit above the atmosphere can look down on auroras from above, seeing their full extent and structure in ways that are impossible from the ground. These overhead views reveal that the auroral oval is not a perfect ring, but an irregular band that shifts and pulses, with bright patches and dark regions, with streamers and arcs that extend and contract over the course of minutes. Some satellites carry instruments that can measure the particles themselves, flying through the regions where auroras are being generated and directly sampling the electrons and ions responsible for the light. These measurements have shown that auroral particles can have a wide range of energies, from a few electron volts to tens of thousands of electron volts. The higher energy particles penetrate deeper into the atmosphere, creating lower altitude auroras with different colours. The lower energy particles are stopped higher up. By combining measurements from many different instruments, ground-based, airborne and space-based, scientists can build up a three-dimensional picture of an aurora, understanding not just what it looks like, but how it's produced, what particles are involved, where they came from, and how they were accelerated. One particularly interesting finding from this research is that auroras are not evenly distributed in time. They tend to occur in bursts, with periods of enhanced activity followed by quieter periods. These bursts are related to substorms, which are episodes of energy release in the magnetotail. During a substorm, the aurora suddenly brightens and becomes more active, often spreading toward the equator and developing rapid motions and complex structures. The substorm then gradually subsides over the course of an hour or so, and the aurora returns to a quieter state. Substorms can occur several times during a single night, creating a rhythm of activity and calm. The triggers for substorms are still being studied, and while the basic outline is understood, energy builds up in the magnetotail and is released through magnetic reconnection. The details of when and why a substorm begins are complex and not fully predictable. The magnetotail itself is a fascinating structure. It's created by the solar wind dragging Earth's magnetic field lines downwind, stretching them out into space like a windsock. The magnetotail has two lobes, a northern lobe and a southern lobe, separated by a current sheet where the magnetic field reverses direction. This is a region of particular interest because it's where reconnection often occurs. When reconnection happens in the magnetotail, it releases energy that drives particles earthward, and some of those particles end up creating auroras. But reconnection is a complex process, involving the rearrangement of magnetic field lines on very small scales so small that they require specialized instruments and sophisticated simulations to study. Understanding reconnection is not just important for understanding auroras, it's important for understanding magnetic phenomena throughout the universe, from solar flares to the dynamics of distant astrophysical plasmas. Auroras also have a seasonal variation that's not immediately obvious. You might think that auroras would be equally common throughout the year, but observations show that they're actually more frequent around the equinoxes, the spring and fall, than around the solstices, the summer and winter. This is called the Russell-McFerran effect, and it has to do with the orientation of Earth's magnetic field relative to the magnetic field carried by the solar wind. During the equinoxes, the geometry is more favourable for the solar wind magnetic field to couple efficiently with Earth's magnetic field, allowing more energy to be transferred into the magnetosphere. During the solstices, the geometry is less favourable, and while auroras still occur, they're somewhat less frequent. This effect is subtle, and there are many other factors that influence aurora activity, but over long periods and large data sets, the equinoctial enhancement is clearly visible. The Earth's magnetic field is not static, it changes over time. On short timescales, it responds to the solar wind, being compressed and stretched and disturbed by geomagnetic storms. On longer timescales, it has its own internal dynamics. The magnetic poles wander slowly over decades and centuries, and occasionally over thousands or millions of years, the magnetic field reverses entirely, with north and south swapping places. During a reversal, the field weakens and becomes more complex, and it's thought that auroras might appear at unusual latitudes or have different characteristics. However, no human has ever observed a magnetic field reversal. The last one happened about 780,000 years ago, long before modern humans existed. What would auroras look like during a reversal? We can only speculate using computer models and theoretical understanding, but it's an intriguing question. The fact that other planets have auroras tells us that the basic physics of auroras is universal. Wherever you have a magnetic field, an atmosphere or at least some source of neutral particles, and a source of energetic charged particles, you can have auroras. On Jupiter, the auroras are driven partly by the solar wind and partly by volcanic material from Io that gets ionized and caught in Jupiter's magnetic field. On Saturn, interactions with the rings and moons add complexity to the auroral processes. On Uranus and Neptune, the magnetic fields are tilted at extreme angles relative to the planet's rotation axis, creating auroral patterns that are quite different from Earth's. Studying these alien auroras helps us understand the diversity of magnetospheric systems and tests our theories in environments very different from Earth. Even some moons have auroras. Ganymede, one of Jupiter's large moons, has its own small magnetic field, and it experiences auroras when particles from Jupiter's magnetosphere interact with that field. This makes Ganymede the only moon in the solar system known to have its own auroras, a unique status that highlights the importance of magnetic fields in creating these light displays. Without a magnetic field, a moon or planet can still have airglow, a faint luminescence from chemical reactions in the atmosphere, but it won't have the structured, dynamic auroras that we see on magnetized bodies. Back on Earth, the study of auroras has also led to advances in related fields. Understanding how particles are accelerated in the magnetosphere has applications to understanding particle acceleration elsewhere in the universe, such as in supernova remnants or around black holes. Understanding magnetic reconnection in Earth's magnetotail has informed studies of reconnection in solar flares and in laboratory fusion experiments. The techniques developed for remote sensing of auroras, using optical instruments, radar and satellites, have been adapted for studying other atmospheric and space phenomena. In science, understanding one thing often leads to understanding many things, as the same physical principles apply in different contexts. There's also a human dimension to aurora science. The scientists who study auroras are people with their own motivations and passions. Many of them were inspired to enter the field because they saw an aurora and wanted to understand it. They've spent years, sometimes decades, building instruments, analysing data, writing papers, and piecing together the puzzle of how auroras work. They've stood on frozen tundra deploying equipment. They've flown on research aircraft through auroral arcs. They've launched sounding rockets to sample the upper atmosphere. They've written computer codes to simulate magnetospheric dynamics. Their work is a testament to human curiosity, to the drive to understand the natural world not for immediate practical gain, but simply because it's there, because it's fascinating, because knowing is better than not knowing. For the rest of us who may not be scientists, auroras offer something different but equally valuable. They offer beauty, wonder, and a sense of connection. When you stand beneath an aurora, you're standing beneath a phenomenon that links you to the sun, to the Earth's interior where the magnetic field is generated, to the thin upper atmosphere, to the solar system and the cosmos beyond. You're part of a planet in motion through space, constantly bathed in the solar wind, protected by a magnetic shield, home to an atmosphere that can light up when energized. This perspective, this sense of context and connection, is something that's easy to lose in daily life. Auroras restore it, at least for a moment, and there's a timelessness to auroras. The aurora you see tonight is the same phenomenon that people saw 1,000 years ago, 10,000 years ago, 1,000,000 years ago. The details change, the solar wind fluctuates, the magnetic field drifts, the atmosphere evolves slowly over geological time, but the basic process is the same. Auroras are ancient, recurring, part of the fabric of Earth's existence. They'll still be happening long after we're gone, long after human civilization is a distant memory, as long as the sun continues to shine and Earth retains its magnetic field and atmosphere. There's something comforting in that continuity, a reminder that we're part of something much larger and longer lasting than our individual lives. When you think about auroras in this way, as part of deep time and cosmic processes, they become more than just pretty lights. They become a link to the past and the future, a manifestation of forces that have shaped our planet and will continue to shape it. The same solar wind that creates auroras also plays a role in the long-term evolution of planetary atmospheres. On Mars, which lost its global magnetic field early in its history, the solar wind has been slowly stripping away the atmosphere over billions of years. On Earth, our magnetic field protects us from this fate, deflecting the solar wind and preserving our atmosphere. Auroras are a side effect of that protection, a visible reminder that we live on a shielded world. The colours of an aurora, too, carry information about the state of the atmosphere. The green line from oxygen, at 557.7 nanometers, is one of the most studied features in atmospheric physics. It's called a forbidden transition because it's very unlikely to occur under normal conditions. The oxygen atom has to remain undisturbed for almost a full second before it can emit this particular wavelength. In denser parts of the atmosphere, the atom would collide with another particle long before it had a chance to emit the green light. But at auroral altitudes, the air is so thin that collisions are rare enough for the forbidden transition to happen. This is why the green line is so prominent in auroras but rarely seen at lower altitudes. It's a signature of the thin, rarefied air of the thermosphere. The red line from oxygen, at 630 nanometers, requires even longer for the atom to emit, about 2 minutes of remaining undisturbed. This means it only shows up at even higher altitudes, above about 200 kilometers, where the air is extremely thin. When you see red in an aurora, you're seeing light from a very high, very rarefied part of the atmosphere, a region that's more space than air. The fact that we can see this light at all from the ground, from hundreds of kilometers away, is remarkable. The atmosphere at those altitudes is so tenuous that a handful of air would contain only a few million molecules compared to trillions per handful at sea level. And yet, when energized, even that thin scattering of atoms can glow brightly enough to be visible to the naked eye. Nitrogen contributes its own set of spectral lines, creating blues and purples, especially at lower altitudes. Nitrogen molecules can be excited in different ways, leading to different emission lines, and the mix of these lines determines the exact shade you see. Sometimes nitrogen creates a deep purple red at the lower edges of auroral curtains, sometimes a blue or violet tinge. The exact colour depends on the energy of the incoming particles and the density of the atmosphere at that altitude. It's a complex chemistry, with dozens of possible reactions and transitions, all happening simultaneously, all contributing to the overall glow. There's also a phenomenon called auroral kilometric radiation, which is radio emission generated by auroras. It's not visible to the eye and can't be heard with the ear, but it can be detected by radio receivers. This radiation is produced by the same population of electrons that creates the visible aurora, but through a different mechanism involving the interaction of the electrons with the magnetic field. Auroral kilometric radiation can be quite strong and can actually be detected from space, allowing satellites far from Earth to monitor auroral activity. It's one more piece of the puzzle, one more way that auroras manifest, extending beyond the visible spectrum into radio waves. In recent years, citizen scientists have contributed to aurora research in meaningful ways. Amateur photographers capture auroras from locations around the world, providing data on timing, location, and appearance that complement scientific observations. Some projects invite people to submit their aurora photos along with metadata about when and where they were taken, and this crowdsourced data helps scientists track the movement and evolution of auroral displays over large geographic areas. Other projects use networks of cameras operated by volunteers to monitor the sky continuously, creating time-lapse records of auroral activity. This collaboration between professional scientists and interested amateurs is a reminder that science is not just for experts in laboratories. It's for anyone with curiosity and a willingness to observe carefully. There are also aurora apps and websites that provide forecasts and alerts. These services use real-time data from satellites and ground stations to predict when and where auroras are likely to be visible. They can send notifications to your phone when conditions look promising, helping you decide whether it's worth venturing out to try to see an aurora. The forecasts are based on measurements of the solar wind taken by spacecraft positioned upstream of Earth, at a point called L1 where the gravitational pull of the Sun and Earth balance out. These spacecraft can see the solar wind about an hour before it reaches Earth, giving forecasters a short but useful warning time. If the solar wind is carrying a southward-pointing magnetic field, conditions are favourable for auroras because that orientation couples well with Earth's northward-pointing field, allowing energy transfer. If the magnetic field is pointing northward, coupling is less efficient and auroras are less likely. The forecasting of auroras has improved significantly over the years, but it's still not perfect. Space weather is inherently unpredictable in some ways because it depends on processes happening on the Sun and in the magnetosphere that we can't control or predict with complete accuracy. A CME might arrive earlier or later than expected. Its magnetic field orientation might change as it travels through space. Reconnection in the magnetotail might start suddenly, or might fail to start at all. These uncertainties mean that aurora forecasts are probabilistic rather than deterministic. They can tell you that conditions are likely to be favourable, but they can't guarantee that you'll see an aurora. This is part of the adventure, part of the reason aurora watching requires patience and a bit of luck. Some of the most memorable auroras are the ones that appear unexpectedly, when you weren't planning to watch for them. You step outside for an unrelated reason, and there it is. A glow in the sky, a curtain forming overhead. These surprise auroras have a special quality because they're not anticipated, not planned for. They're a gift, a reminder that the natural world operates on its own schedule and sometimes offers beauty when you're not even looking for it. Many people have stories like this, of seeing their first aurora by accident, of being in the right place at the right time without even knowing that auroras were possible. The experience of seeing an aurora can vary tremendously, depending on where you are and what the conditions are like. An aurora seen from the middle of a city, fighting against light pollution, might be just a faint glow, barely distinguishable from the general sky brightness. The same aurora seen from a dark location in the countryside can be vivid and detailed, with clear colours and structure. An aurora at the edge of the auroral oval, just barely visible on the horizon, is a different experience from an aurora directly overhead, filling the sky from horizon to horizon. A quiet, steady arc is different from a fast-moving, pulsating display. All of these are auroras, all valid, all beautiful in their own way, but they offer different experiences. There's also a difference between watching an aurora alone and watching one with others. Watching alone can be meditative and personal, a one-on-one encounter with nature. Watching with friends or family can be social and shared, with exclamations and pointing, and the joy of experiencing something remarkable together. Watching with a group of strangers, perhaps at a popular viewing location, can create a sense of community, a feeling that you're all witnesses to the same event, all connected by the shared experience. There's no right way to watch an aurora. It depends on your temperament and the circumstances. For some people, the appeal of auroras is primarily aesthetic. They're drawn to the beauty, the colours, the motion, the visual spectacle. For others, the appeal is more intellectual, rooted in an appreciation for the science and a desire to understand the mechanisms. For still others, the appeal is emotional or even spiritual, a sense of awe and wonder that connects them to something larger than themselves. All of these responses are valid, and they're not mutually exclusive. You can appreciate the beauty and the science and the sense of wonder all at the same time. In fact, understanding the science often enhances the sense of wonder rather than diminishing it. Knowing that the green light comes from oxygen atoms relaxing from an excited state doesn't make the green any less beautiful, it makes it more meaningful. As the night deepens and the aurora continues its dance, there's a rhythm to watching that settles in. Your eyes adjust to the darkness, your body adjusts to the cold, and your mind enters a state of quiet attention. You're not thinking about your daily concerns or your plans for tomorrow. You're simply present, watching the sky, noticing the changes, the brightening and dimming, the shifts in colour and form. This kind of present moment awareness is rare and valuable. It's a form of meditation, though you might not think of it that way. You're anchored in the here and now by the aurora itself, which demands nothing from you except attention. Time can seem to stretch during an aurora display. Minutes feel longer, hours pass without notice. You might think you've been outside for 20 minutes when it's actually been an hour, or you might feel like you've been watching for ages when it's only been a few minutes. This distortion of time perception is common during absorbing experiences, and it's another sign that watching an aurora pulls you out of your normal mental state and into something different, something more focused and immediate. Eventually the aurora fades, the particles slow, the energy decreases, the glow diminishes, the curtains soften and dissolve, the arcs fade into the background sky, and the stars, which had been outshone by the aurora, become visible again. The sky returns to its normal darkness and the show is over. This ending is bittersweet. You're grateful to have seen it, but you also feel a sense of loss as it disappears. Many aurora watchers will stay outside even after the aurora has faded, hoping it might return, and sometimes it does. A new surge of particles arrives, a new substorm begins, and the aurora flares up again, giving you a second show. Other times, the sky remains dark, and you know the display is truly over for the night. Walking back inside after watching an aurora, you often feel changed in some small way. It's hard to articulate exactly how, but there's a sense of having witnessed something important, something worth the cold and the late hour and the effort. You carry the memory of it with you, and for days or weeks afterward, you might find yourself thinking about it, replaying the images in your mind, feeling again the quiet awe you felt while watching. These memories can be a source of comfort and inspiration, a reminder that the world holds beauty and wonder if you take the time to look for it. The next story is about to begin. Please relax and enjoy. Welcome to a quiet place. A place where the only task ahead of you is to let your mind wander gently through the soft glow of starlight and to let each thought settle like dust on a calm surface. Tonight, we're going to explore the Milky Way, not as something distant and unreachable, but as the quiet, familiar home it truly is. You're already inside it. Right now, as you rest, you're tucked into one small corner of this vast, slowly turning collection of stars and dust and silent space. There's nothing to do but listen and breathe and let these small facts drift past you like clouds across a dark sky. We'll move through exactly 100 gentle observations about the Milky Way. Small pieces of understanding, each one simple enough to hold for a moment before releasing it. There's no hurry, there's no test. There's only the soft rhythm of learning, like counting stars until the counting itself becomes a kind of rest. So settle in, let your breathing slow. Picture, if you can, a pale river of light stretched across a perfectly dark sky, a band of softness against the black. That image, that quiet glow, is where we'll spend our time tonight. The Milky Way is the galaxy that contains our solar system. This is the first fact, and perhaps the most grounding. When you look up on a clear, dark night and see that hazy band stretching overhead, you're not looking at something separate from yourself. You're looking at the structure you're already part of. The Milky Way isn't a distant object in the sky. It's the neighborhood. It's home. Our sun, our Earth, the moon, all the planets, every comet and asteroid and speck of dust in our solar system. They all belong to this one galaxy. The Milky Way is the cosmic address that holds everything familiar to us. A galaxy is a vast collection of stars, gas, dust, and dark matter held together by gravity. To understand the Milky Way, it helps to understand what a galaxy is in the first place. Imagine gathering hundreds of billions of stars, more stars than you could count in many lifetimes, and letting gravity pull them into a single organized structure. But it's not just stars. Between the stars, there's gas, mostly hydrogen, drifting in enormous clouds. There's dust, made of tiny solid particles scattered throughout, and woven through everything, invisible but essential, is dark matter, a kind of mass that doesn't emit light, but whose gravity helps hold the whole structure together. All of this, bound by the patient, inexorable pull of gravity, forms what we call a galaxy. From Earth, we see the Milky Way as a hazy band because we're viewing it from inside. This is one of those facts that feels almost strange once you think about it. If you were outside the Milky Way, looking back from a great distance, you might see it as a beautiful spiral, arms of stars curving outward from a bright centre. But we don't have that view. We're embedded in the structure itself, sitting somewhere in the disk, looking along the plane. So when we look toward the densest parts of the galaxy, what we see is a band, a soft milky stripe, because we're seeing the combined light of countless stars stretching away in both directions. It's like standing in the middle of a forest and looking horizontally through the trees. You see depth, layers, a sense of many trunks receding into shadow. That's the view we have of our own galaxy. That hazy glow is the combined light of many distant stars. Each point of light you can resolve individually as a single star, probably relatively nearby in cosmic terms. But the soft glow, the diffuse brightness that makes the band look like spilled milk, that comes from stars too far away or too faint to see as separate points. Your eye blends them together into a continuous shimmer. It's a visual echo of distance, of sheer number. There are so many stars along those sightlines that their light merges, creating that gentle, pervasive glow. The band looks brightest, where the star density is highest. This makes sense once you think about it, but it's worth savouring. The Milky Way isn't uniformly bright. Some parts of the band are richer, more luminous. Those are the directions where stars are more tightly packed, where the disk is thicker, or where we're looking through more layers of the galaxy's structure. Other parts are dimmer, either because there are fewer stars in that direction, or because dust is blocking the light. The variation is subtle, but if you've ever watched the Milky Way on a truly dark night, you've seen how it swells and fades, how certain regions seem to glow more intensely, while others are almost ghostly. Milky Way is a name inspired by its soft spilled light appearance. The name itself is ancient, though the exact origins vary by culture. In English, Milky Way evokes the image of milk poured across a dark surface, an apt metaphor for that pale, clouded band. Other cultures have called it a river, a path, a bridge. The common thread is softness, a sense of something flowing or spilled or gently laid across the heavens. It's a name that invites calm. There's nothing harsh about it. It's not the blazing belt or the fierce stripe. It's milky, quiet, almost comforting. The galaxy has a flattened disk shape rather than a perfect sphere. If you could step outside and view the Milky Way edge-on, you'd see that it's quite thin relative to its width. Imagine a dinner plate, or better yet, two dinner plates placed rim to rim with a slight bulge in the middle. That's closer to the Milky Way's shape than a ball or a cloud. Most of the stars, especially the younger ones, are organised into this flat disk. The disk rotates slowly, and that rotation helps maintain its flatness. It's a consequence of angular momentum and gravity working together over billions of years. The disk contains many of the stars we can see in the night sky. When you look up and pick out individual stars, Sirius, Vega, Betelgeuse, most of those are part of the Milky Way's disk. They're our neighbours in this vast structure. Some are closer, some farther, but they share the same general plane, the same galactic environment. The disk is where much of the galaxy's visible activity happens, where new stars are born, where spiral arms wind slowly outward. The Milky Way also has a central bulge of stars. At the very heart of the galaxy, the disk thickens into a bulge, a more densely packed region of stars. These stars are often older, redder, having burned for billions of years. The bulge is brighter than the outer disk, though from Earth, dust often obscures our view of it. If you could see through all that dust, the central bulge would dominate the view, a warm glow at the galaxy's core. Surrounding everything is a large, faint halo. The halo is less obvious, harder to see, but it's there. A vast, roughly spherical region that extends far beyond the disk. The halo contains old stars, ancient star, clusters, and is thought to hold much of the galaxy's dark matter. It's like a diffuse envelope around the more structured disk and bulge, a reminder that the Milky Way's influence extends far beyond its bright, visible parts. Just one more small fact, and then we drift. Our solar system sits inside the Milky Way's disk. This is your location, cosmically speaking. You're not in the halo, not in the central bulge, but in the disk, somewhere in the suburbs of the galaxy, you might say. The disk is where the action is, where gas and dust provide the raw materials for new stars, where spiral arms trace slow patterns. You're embedded in that environment, part of that ongoing story. We're not near the very centre of the galaxy. In fact, we're quite far out. The galactic centre lies roughly 26,000 light-years away, a distance so vast that light from the centre, travelling at its tremendous speed, takes 26,000 years to reach us. We're out in a quieter region, away from the crowded, energetic core. This is probably fortunate. The centre is a busy, intense place, full of tightly packed stars and powerful forces. Out here, there's more room, more calm. We orbit the galactic centre like a slow, wide carousel. Just as Earth orbits the Sun, and with it, our entire solar system, orbits the centre of the Milky Way. It's a grand, sweeping orbit, far larger and slower than anything we experience in our daily lives. We're moving through space at a speed of roughly 200 kilometers per second relative to the galactic centre, but the orbit is so large that it takes an immense amount of time to complete even one circuit. This orbit takes a very long time compared with a human life. Estimates suggest it takes about 200 to 250 million years for the Sun to make one full orbit around the galaxy. This span of time is called a galactic year, or sometimes a cosmic year. To put that in perspective, the last time the Sun was in this exact spot in its orbit, dinosaurs had not yet appeared on Earth. The whole history of human civilization is a tiny fraction of one galactic orbit. The Milky Way's rotation is a deep, slow rhythm, far removed from the pace of human experience. Even while you lie still, Earth is moving through space. Right now, as you rest, you're travelling. Earth is spinning on its axis, orbiting the Sun, and the Sun is carrying you along on its orbit around the galaxy, and the galaxy itself is moving relative to other galaxies. There are layers of motion, each one imperceptible in the moment, but real and ongoing. It's a gentle thought, really. You don't have to do anything to be part of this motion. You're already moving, already journeying through space, even in stillness. That motion is shared. Planets, stars, and gas all drift together. The Sun doesn't orbit alone. It carries its planets, its asteroids, its distant comets, all moving together as a single family. And nearby stars are doing the same, each one following its own orbit, all of them drifting along together like a slow-moving river. The Milky Way is not a rigid structure. It's a dynamic flow of matter, each piece responding to gravity's pull, each orbit contributing to the whole. The Milky Way is so large that here and there can be separated by vast distances. The galaxy is roughly 100,000 light-years across, a span so enormous that it defies easy comprehension. If you could send a message at the speed of light from one side of the galaxy to the other, it would take 100,000 years to arrive. Within that expanse, stars are separated by light-years, sometimes many light-years. Space is not crowded. There's room, emptiness, silence between the points of light. Most stars you see are relatively nearby in galactic terms. When you look at the night sky and see individual stars, you're mostly seeing stars that are within a few hundred or a few thousand light-years of Earth. That might sound like a lot, but in a galaxy 100,000 light-years wide, it's the immediate neighbourhood. The vast majority of the Milky Way stars are too far away to resolve individually with the naked eye. They contribute to that diffuse glow, but they don't stand out as separate points. Many stars in the Milky Way are too faint to see with the naked eye. Even the brightest star in the galaxy would appear faint if it were far enough away. And most stars are not especially bright to begin with. Small, dim, red stars outnumber the bright, massive ones. These dim stars, red dwarfs for example, can shine steadily for trillions of years, but they're so faint that even relatively nearby ones can be invisible without a telescope. The Milky Way is full of these quiet, unassuming stars, far more numerous than the brilliant giants we notice. Night skies look different depending on dust, light pollution, and your location. If you've ever seen the Milky Way from a truly dark site, far from city lights under clear skies, you know how striking it can be. But light pollution washes out that view for much of the world. Dust in Earth's atmosphere can also scatter light and reduce contrast. And your latitude matters too. From some locations, certain parts of the Milky Way are always below the horizon. The view is variable, a reminder that what you see is shaped by where you are and what conditions allow. Just one more small fact, and then we drift. The Milky Way band is brightest in truly dark skies. This is worth emphasizing because it's becoming rarer. As artificial light spreads, fewer people have the chance to see the Milky Way in its full glory. But in places far from human lights, where the sky is a vault of pure darkness, the Milky Way can be astonishingly bright. It can cast faint shadows. It can dominate the sky, a river of light stretching from horizon to horizon. That brightness is a measure of how many stars there really are, and how much light they produce when nothing interferes with the view. The band is made of countless unresolved stars. Each time we say this, it's worth pausing on the word countless. Not uncountable in principle. Someone with enough patience and a good telescope could catalogue them, but countless in the practical sense. Too many to keep track of, too many to name, too many to ever know individually. They blend together, and in that blending they create something beautiful. A collective glow that represents the shared light of billions. Dark lanes in the band are clouds of dust blocking starlight. If you've seen detailed images of the Milky Way, you've probably noticed dark patches, gaps in the glow. These aren't empty regions. They're clouds of dust thick enough to block the light of stars behind them. The dust particles themselves are tiny, far smaller than grains of sand, but there are so many of them, spread across such vast volumes that they can dim or completely obscure starlight. These dark lanes give the Milky Way texture, depth, a sense of structure. Dust doesn't turn off stars, it simply hides their light from our view. This is an important distinction. The stars behind those dark clouds are still there, still shining. They haven't been extinguished. It's just that their light, travelling through space, encounters dust along the way, and that dust absorbs or scatters the light before it can reach us. From another angle, from a different vantage point, those same stars might be perfectly visible. It's a matter of perspective, of what lies between the observer and the source. The galaxy's disk is filled with gas and dust along with stars. The Milky Way is not a sterile environment. Between the stars there's material, mostly hydrogen gas, but also dust, molecules, heavier elements. This interstellar medium, as it's called, is incredibly diffuse by everyday standards, far more tenuous than the best vacuum we can create on Earth. But over the vast distances of space, even that thin, material adds up. It's the raw material for new stars, and it also shapes what we see when we look through the galaxy. Dust grains are tiny, but there are so many that they can dim light across huge regions. A single dust grain is microscopic, perhaps a fraction of a micrometer across. But space is vast, and when you look through a cloud of dust, you're looking through countless trillions of these grains. Each one scatters or absorbs a tiny bit of light. Collectively, they can reduce starlight significantly, reddening it and dimming it or blocking it entirely. It's a reminder that even the smallest things, given enough numbers and enough space, can have profound effects. When you see a rift in the Milky Way, you're often seeing dust silhouettes. The Great Rift, for example, is a prominent dark lane that runs along much of the Milky Way's length in the summer sky, as seen from the northern hemisphere. It's not a gap in the stars. It's a foreground curtain of dust blocking the light of more distant stars. The rift has structure, texture, because the dust clouds have structure. They're not uniform blankets, they're clumpy, filamentary, shaped by gravity and magnetic fields and the motions of gas. The band arches across the sky because we're inside a disk looking along its plane. This is another consequence of our location. The disk of the Milky Way is oriented in space, and from Earth, that orientation makes the band appear to curve across the sky. In some seasons the band is higher, in others lower or barely visible, but its arching path is always a reflection of the disk's geometry and our place within it. If we could step outside and view the galaxy from above or below, the disk would appear flat, but from inside it arches. Looking away from the plane, the sky can look darker and more open. If you're under a dark sky and you look toward a direction perpendicular to the Milky Way's plane, you're looking out of the disk toward intergalactic space. There are fewer stars in that direction, less foreground material. The sky appears darker, more empty, though of course it's not truly empty. There are still stars and beyond them, distant galaxies. But the density drops, and the visual effect is one of openness, of looking out rather than through. The Milky Way is less a stripe on the sky, and more the structure you're inside. This shift in perspective is subtle but important. The Milky Way isn't painted on the sky like a decoration. It's the environment. You're not looking at it from the outside, you're looking through it, around it, within it. Every direction you look, you're seeing some part of the Milky Way, some density of stars and dust. The band is just the direction where that density is highest, where the view extends deepest into the structure. Just one more small fact, and then we drift. The Milky Way has spiral structure, like gently curved lanes. If you could view the Milky Way from above, you'd see that it's not just a featureless disk. It has arms, spiral arms, curving outward from the central regions like the arms of a pinwheel. These arms aren't solid objects. They're regions where stars and gas are more concentrated. The spiral pattern rotates, though not like a solid wheel, is more like a wave, a pattern that moves through the disk, organising stars and gas into these graceful curves. Spiral arms are regions where gas and stars are more concentrated. Think of the arms as traffic jams in the disk. Material moves into the arms, slows down due to gravity, and piles up. This increased density makes the arms brighter, easier to see. They're also where much of the star formation happens, because the higher density helps trigger the collapse of gas clouds into new stars. The arms are dynamic, evolving, a sign that the galaxy is not static but actively shaping itself. Arms are not solid objects, but patterns within a rotating disk. This is one of those concepts that takes a moment to grasp. You might imagine the spiral arms as fixed structures, like the blades of a fan rotating together. But that's not quite right. The arms are density waves, patterns that move through the disk at a different speed than the stars themselves. A star might pass into an arm, spend some time in that denser region, and then pass out the other side. The arm persists, but the material within it changes. It's a dynamic equilibrium, a pattern that endures even as the individual pieces flow through it. The central bulge is a thicker, brighter region of stars. If the disk is a flat plane, the bulge is a swelling at the centre, a concentration of stars in a more spherical or elliptical shape. The bulge is old, dense and bright. It contains a huge number of stars packed more tightly than in the outer disk. If you were somehow able to stand near the galactic centre, ignoring all the practical impossibilities, the night sky would be astonishingly bright, filled with stars visible in every direction. The bulge contains many older stars. The stars in the bulge tend to be redder, cooler, older. They were born long ago in the early history of the galaxy, and they've been orbiting the centre ever since. These are not the hot, blue, short-lived stars you might find in active star-forming regions. They're the long-lived survivors, stars that have settled into a slow, steady burn, contributing their warm light to the bulge's glow. A halo extends beyond the main disk in all directions. The halo is harder to visualize because it's so diffuse and faint. It's not a sharp boundary. It fades gradually into the darkness of intergalactic space. But it's there, a vast region surrounding the disk and bulge, containing old stars, globular clusters, and a lot of dark matter. The halo is ancient, a relic of the galaxy's formation, and it extends far beyond the visible parts of the Milky Way. The halo contains older stars and star clusters. The stars in the halo are among the oldest in the galaxy, some approaching the age of the universe itself. They're metal poor, meaning they have fewer heavy elements than younger stars, because they formed before many generations of stellar recycling had enriched the galaxy with heavier elements. The globular clusters, tight spherical groups of stars, are particularly prominent in the halo, each one a dense community of ancient suns. The halo is also where much of the galaxy's dark matter is thought to be. Dark matter doesn't emit light, so we can't see it directly, but we can infer its presence from the way visible matter moves. The rotation curve of the Milky Way, how fast stars and gas orbit at different distances, suggests there's much more mass than we can see. That missing mass is thought to be dark matter, and much of it resides in the halo, forming a vast invisible reservoir that helps bind the galaxy together. The Milky Way is not a static shape. It slowly changes over time. Galaxies are dynamic. Stars are born, stars die. Gas flows in and out. Gravity shapes and reshapes the structure. The Milky Way you see tonight is not exactly the Milky Way of 1 billion years ago, nor the one that will exist 1 billion years hence. The changes are slow, imperceptible on human timescales, but they're real. The galaxy is evolving, growing, responding to the forces acting on it. Gravity quietly organises everything into these large-scale forms. Behind all this structure, spiral arms, bulge, halo, disk, is gravity. Gravity pulls matter together, sets it spinning, flattens it into a disk, concentrates it into a bulge. Gravity holds stars in orbit, keeps gas clouds from dispersing, binds clusters together. It's the organising principle, the invisible hand shaping the galaxy, and it does all this quietly, without fanfare, just the patient, inexorable pull of mass on mass. Just one more small fact and then we drift. The galactic centre lies in the direction of the constellation Sagittarius. From Earth, if you look toward Sagittarius during the summer months, in the northern hemisphere, you're looking toward the heart of the Milky Way. The centre itself is hidden by dust, so you can't see it directly with visible light, but that direction is where the core lies, roughly 26,000 light-years away. It's a helpful anchor, a way to orient yourself when you look at the night sky. The centre is crowded with stars, gas and dust. The galactic centre is not a calm, empty place. It's a dense, energetic region where stars are packed closely together and where immense clouds of gas and dust swirl. The environment there is extreme by our standards. More radiation, stronger gravity, more frequent interactions between stars and clouds. It's the bustling downtown of the galaxy, contrasting sharply with the quieter suburbs where we reside. It's difficult to see directly in visible light because dust blocks the view. If you tried to observe the galactic centre with an ordinary telescope using visible light, you'd be disappointed. The view is obscured by intervening dust clouds, which absorb and scatter the light from the centre. This is why early astronomers, limited to visible light, had trouble understanding the galaxy's structure. They could see the Milky Way band, but the center remained hidden. Infrared and radio observations help us see through dust. Fortunately, light comes in many forms, and some wavelengths pass through dust more easily than others. Infrared light, with its longer wavelength, can penetrate dust clouds that block visible light. Radio waves can do the same. By observing the galactic center in these wavelengths, astronomers have been able to map its structure, identify individual stars, and study the gas and dust there. It's a reminder that seeing isn't always about visible light. Sometimes you have to look in other ways. At the center is a supermassive black hole called Sagittarius A. This is one of the most striking discoveries in modern astronomy. At the very heart of the Milky Way, there's a black hole, not a small one formed from a single collapsing star, but a supermassive black hole with a mass about 4 million times that of the Sun. It's called Sagittarius A, or SEGR, just for short. The asterisk is part of the name, a convention from radio astronomy. This black hole is the anchor point of the galaxy, the gravitational center around which everything else orbits. A supermassive black hole can be calm for long periods. Despite its fearsome reputation, a black hole doesn't reach out and grab things. It just sits there, exerting gravity like any other mass. SGRA is relatively quiet at the moment. It's not actively consuming large amounts of material, so it's not blazing with radiation. Occasionally gas or a star might venture too close and fall in, producing a brief flare of energy, but much of the time the black hole is simply there, silent and still, a dense point of gravity. The center region has intense gravity because of all its mass. The combination of the black hole and the dense packing of stars creates a region of very strong gravity. Stars near the center orbit much faster than stars farther out. Some stars have been observed whipping around SGRA at a significant fraction of the speed of light, completing an orbit in just a few years, a stark contrast to the Sun's 200 million year orbit. That speed is a measure of the gravitational pull, a sign of how much mass is concentrated there. Stars near the center orbit rapidly compared with our neighborhood. If you could watch the galactic center over years or decades, you'd see stars moving noticeably against the background. This is unusual. Most stars are so far away that their motion is imperceptible over a human lifetime. But near SGRA, orbits are tight and fast, and astronomers have tracked individual stars moving in elliptical paths around the black hole. These observations have been crucial in confirming the black hole's existence and measuring its mass. The galactic center is far away, like a distant lighthouse you don't need to approach. It's worth pausing on this image. The galactic center is important, central to the galaxy's structure and dynamics, but it's also remote. You don't have to worry about it. Its gravity affects the large-scale motion of the galaxy, but from 26,000 light-years away, its influence on the solar system is negligible. It's a distant anchor, a point of reference, but not something that reaches into our local space. It can be thought of as the quiet hub of our galaxy's slow turning. The center is where the rotation is anchored, where the galaxy's mass is most concentrated. Everything orbits around it, layer upon layer, from the innermost stars whipping around in years to the outermost halo objects taking hundreds of millions of years. The center doesn't rush. It doesn't need to. It simply is, a focal point, a hub, the still point in the turning galaxy. Just one more small fact, and then we drift. The Milky Way's arms contain many regions where new stars form. The spiral arms are not just brighter because they contain more stars, they're brighter because they're actively making new stars. Star formation tends to happen in the arms because that's where gas clouds are compressed, where conditions are right for gravity to pull clouds into collapse. These regions are often marked by glowing nebulae, clouds of gas lit up by the ultraviolet light of young, hot stars. Stars form when cold gas clouds collapse under gravity. Star formation is a process driven by gravity. A cloud of cold gas, often molecular hydrogen, sits in space. If a region within that cloud becomes dense enough, gravity begins to pull it together. As it collapses, it heats up, eventually becoming so hot and dense that nuclear fusion ignites in the core. A star is born. The process is slow, taking perhaps a few million years from the initial collapse to a stable, shining star, but the end result is the same, matter becoming light. These clouds are often called molecular clouds. Molecular clouds are the nurseries of stars. They're vast regions of space filled with gas and dust, cold enough that atoms combine into simple molecules, hence the name. Hydrogen molecules, H2, carbon monoxide, water and many other molecules have been detected in these clouds. The cold temperatures and high densities make them ideal places for star formation. Some molecular clouds are enormous, containing enough material to form thousands or even millions of stars. Dust within clouds helps them cool and clump together. Dust plays a crucial role in star formation. The dust grains within a molecular cloud can absorb and re-radiate energy, helping the cloud lose heat. As the cloud cools, it becomes easier for gravity to pull it together. Without cooling, the cloud's internal pressure would resist collapse. Dust also provides surfaces where molecules can form, and it shields the interior of the cloud from disruptive radiation. In these ways, dust is not just an obstruction, it's a facilitator helping stars come into being. Star-forming regions can glow when nearby stars energize the gas. Once a few stars have formed within a cloud, especially if they're massive and hot, their radiation can ionize the surrounding gas, stripping electrons from atoms. The ionized gas glows, emitting light in specific colors determined by the elements present. These glowing regions are called emission nebulae, or H2 regions, ionized hydrogen regions. They're some of the most beautiful sights in the galaxy. Brilliant clouds of red, pink and blue, each one a sign that new stars have ignited and are lighting up their surroundings. Many bright nebulae are visible signs of star birth. The Orion Nebula, for example, is a famous star-forming region, easily visible to the naked eye as a fuzzy patch in Orion's sword. Within that nebula, stars are being born right now. Telescopes reveal young stars, still surrounded by the remnants of their birth clouds, and protostars still in the process of collapsing. These nebulae are dynamic, evolving. Over millions of years, the stars will disperse the remaining gas, and the nebula will fade, leaving behind a new cluster of stars. Starbirth is slow, more like a long dawn than a sudden flash. It's important to dispel any notion of star formation as a dramatic explosion. It's not. It's a gradual process. A cloud collapses over millions of years. The protostar grows, gathers mass, heats up. Eventually fusion begins, but even that is a gentle ignition, a slow ramp-up rather than a sudden burst. The star then settles onto what's called the main sequence, where it will spend most of its life steadily fusing hydrogen into helium. The whole process is patient, unhurried, like the galaxy itself. Some stars form in clusters, like neighborhoods turning on their lights together. Not all stars form in isolation. Often a single molecular cloud will give birth to dozens, hundreds or thousands of stars at roughly the same time. These stars born together tend to remain gravitationally bound for at least a while, forming a star cluster. Open clusters, like the Pleiades, are examples of this. Groups of young stars still relatively close together, sharing a common origin. Over time, the cluster may disperse as stars drift apart, but for a time, they're a family, bound by gravity and shared history. Massive stars live shorter lives than small stars. This might seem counterintuitive. Surely a bigger star with more fuel would last longer. But it doesn't work that way. Massive stars burn their fuel much more quickly. They're hotter, brighter, and they fuse elements at a furious rate. A star with 10 times the mass of the Sun might live only a few million years, while a star with half the Sun's mass could shine for tens or even hundreds of billions of years. It's a trade-off. Brightness and brevity versus dimness and longevity. Small stars can shine steadily for extremely long times. The smallest stars, red dwarfs, are the tortoises of the stellar world. They're dim, cool, and they burn their hydrogen fuel so slowly that they can last for trillions of years, far longer than the current age of the universe. None of these stars has ever died of old age because they simply haven't had time. They'll outlast nearly everything, quiet and persistent, shining faintly into the deep future. Just one more small fact, and then we drift. Because we're inside the Milky Way, mapping it is like mapping a forest from within. Imagine standing in the middle of a vast forest and trying to draw a map of it. You can see the trees around you, you can measure distances to nearby landmarks, but much of the forest is hidden by the trees themselves. You have to infer the overall shape from limited views, from patterns and clues. That's the challenge astronomers face with the Milky Way. We can't step outside to get a clear view, so we have to piece together the structure from observations made from our single vantage point. Astronomers use many wavelengths of light to study the galaxy. Visible light is useful, but it's only part of the story. Different wavelengths reveal different aspects of the galaxy. Radio waves show where cold hydrogen gas is concentrated. Infrared light reveals stars hidden by dust and shows the thermal glow of dust itself. X-rays highlight high-energy processes, like gas heated to extreme temperatures. By combining observations across the electromagnetic spectrum, astronomers build a more complete picture of the Milky Way's structure and contents. Radio waves can travel through dust more easily than visible light. This is one of the key advantages of radio astronomy. Dust that would block or scatter visible light is largely transparent to radio waves. This means astronomers can use radio telescopes to observe the galactic center, star-forming regions deep within molecular clouds and other obscured parts of the galaxy. Radio observations have been essential in mapping the spiral arms and understanding the distribution of gas. Hydrogen gas emits a radio signal used to map large structures. Neutral hydrogen, hydrogen that hasn't been ionized, emits radio waves at a very specific wavelength, about 21 centimeters. This emission comes from a subtle quantum transition in the hydrogen atom. Because hydrogen is the most abundant element in the universe, this 21 centimeter line is a powerful tool. By observing it, astronomers can map where hydrogen gas is located throughout the galaxy, tracing out the spiral arms and the large-scale structure of the disk. Infrared light can reveal stars hidden by dust. Dust absorbs visible light but re-radiates that energy in the infrared, so infrared telescopes can see through dusty regions and detect the stars within. Infrared surveys of the Milky Way have uncovered vast numbers of stars, including many cool dim stars that would be nearly invisible in visible light. These observations have helped astronomers understand the true stellar population of the galaxy. Star motions help us understand the galaxy's mass distribution. By measuring how fast stars are moving and in what orbits, astronomers can infer how much mass is present and where it's located. This is similar to how we can deduce the Sun's mass by watching how the planets orbit. If you know how fast something is moving and the radius of its orbit, you can calculate the mass it's orbiting. Applied across the galaxy, this technique reveals the distribution of matter, both visible and dark. If stars move faster than expected, it hints at unseen mass. One of the big surprises in studying galaxies, including the Milky Way, was that stars in the outer regions move faster than they should if only the visible matter were present. According to Newton's laws, stars farther from the center should orbit more slowly, just as outer planets in the solar system orbit more slowly than inner ones. But that's not what we see. Stars far from the galactic center orbit at roughly the same speed as those closer in. This suggests there's additional mass we can't see, providing extra gravitational pull. This is one reason dark matter is included in Milky Way models. To explain the observed motions, astronomers add dark matter to their models. Dark matter doesn't emit light, doesn't interact via the electromagnetic force, but it has mass and therefore gravity. By including a large halo of dark matter surrounding the galaxy, models can match the observed rotation curves. The nature of dark matter is still one of the biggest mysteries in physics, but its presence in the Milky Way is strongly suggested by the evidence. We also map the galaxy by measuring distances to star clusters and special variable stars. Distance measurement is crucial in astronomy, and it's not always easy. For nearby objects, parallax, the apparent shift of a star's position as Earth orbits the Sun, can give direct distance measurements. For more distant objects, astronomers use standard candles, objects with known intrinsic brightness. Certain types of variable stars, like Cepheids, have a relationship between their pulsation period and their luminosity. By measuring the period, astronomers can deduce the luminosity, compare it to the observed brightness, and calculate the distance. Over time, these measurements build a calm, detailed picture of our home. Each observation is a piece of the puzzle. Each distance measurement, each spectrum, each image adds to the understanding. It's slow work, requiring patience and precision, but the result is a growing map of the Milky Way, its size, shape, structure, and contents. And that map is not static. It's constantly refined as new data comes in, as techniques improve, as we learn more about the galaxy we live in. Just one more small fact, and then we drift. Star clusters are groups of stars bound together by gravity. Within the vast expanse of the Milky Way, stars sometimes gather into clusters, tightly knit groups where stars are much closer together than average. Gravity holds these clusters together, resisting the forces that would otherwise pull them apart. Clusters are laboratories for studying stellar evolution, because all the stars in a cluster were born at roughly the same time and from the same material, making it easier to compare them. Some clusters are young and still close to their birth clouds. Open clusters like the Pleiades or the Hyades are relatively young by astronomical standards, often just a few 100 million years old or less. They're often still associated with the nebulae from which they formed, or at least located in regions rich with gas and dust. These clusters are loose, with stars spread over many light years, and they contain stars of various masses, including hot blue massive stars that haven't yet burned out. Others are ancient and live, in the halo. Globular clusters are very different. They're old, dense and spherical, containing tens of thousands to millions of stars packed into a volume just tens of light years across. Globular clusters orbit in the galactic halo, often far from the disk. Their stars are ancient, typically 10 billion years or older, and they're metal poor, meaning they formed when the universe had fewer heavy elements. Globular clusters are relics of the early galaxy, survivors from a time when the Milky Way was still taking shape. Globular clusters are dense, round collections of very old stars. Imagine a spherical swarm of stars, so densely packed that near the centre, stars might be separated by just light days rather than light years. If you could stand on a planet near the centre of a globular cluster, the night sky would be astonishing, filled with thousands of bright stars, possibly enough to cast significant light even at night. Globular clusters are gravitationally stable. They've existed for billions of years and will likely persist for billions more. Open clusters are looser groups, often younger, found in the disk. Open clusters are scattered throughout the Milky Way's disk, especially in the spiral arms where star formation is active. They're less tightly bound than globular clusters, and over time, many of them will disperse as their stars drift apart. Tidal forces from the galaxy can pull stars away, and close encounters with molecular clouds can disrupt the cluster. But while they last, open clusters are beautiful, a reminder that stars are not always solitary. Our sun may have been born in a cluster long ago. This is an intriguing possibility. Most stars form in clusters, so it's likely the sun did too. Early in its life, the sun would have been part of a group of sibling stars, all born from the same molecular cloud. But over 4.5 billion years, those siblings have scattered, drifting apart as they orbit the galaxy. Some might still be out. There, stars with the same chemical composition, the same age, but now separated by vast distances. Astronomers have searched for these solar siblings, but identifying them is difficult because so much time has passed. Over time, clusters can disperse as stars drift apart. Even bound clusters don't last forever. Gravitational interactions, both internal and external, can gradually eject stars from the cluster. Each encounter, each pass near another star or a massive cloud, changes the orbit slightly. Over millions or billions of years, these changes accumulate. Open clusters in particular often disperse within a few 100 million years. Globular clusters last longer because they're more tightly bound, but even they can lose stars over time. The galaxy is full of moving groups that share a common origin. Even after a cluster has dispersed, the stars that once belonged to it continue to share certain characteristics. They have similar motions through space, similar velocities, similar trajectories, because they started out together. They may also have similar chemical compositions, similar ages. Astronomers can identify these moving groups by looking for stars with correlated motions. It's like seeing a group of people walking in different directions but all starting from the same point. You can trace back their paths and infer that they were once together. Even when stars separate, their shared motion can remain as a faint signature. This shared motion is a kind of fossil record, a trace of the past. By studying it, astronomers can learn about the history of star formation in the Milky Way, about how clusters form and dissolve, about the dynamical processes that shape the galaxy. It's a subtle detective work, piecing together history from the faintest of clues. In this way, the Milky Way keeps gentle traces of its own history. The galaxy is not a blank slate. Its current structure reflects its past, the mergers it has undergone, the star formation events that have occurred, the clusters that have formed and dispersed. Every star, every orbit, every chemical abundance is a piece of the story, and by studying these traces, astronomers can read that story, learning how the Milky Way came to be and how it continues to evolve. Just one more small fact, and then we drift. The Milky Way formed long ago from smaller pieces coming together. Galaxies don't spring into existence fully formed. They grow, built up over time as gas, stars, and dark matter accumulate under gravity's pull. The early universe was smoother, more homogeneous, but tiny density fluctuations seeded the growth of structure. Over millions and billions of years, those fluctuations grew, pulling in more matter, forming the first stars, the first galaxies. The Milky Way is one result of that process, a galaxy that has been assembling itself for most of the age of the universe. Galaxies can grow by merging with other galaxies. One of the key processes in galaxy evolution is merging. When two galaxies come close together, gravity can pull them into a dance. They orbit each other, slowly spiraling inward, until eventually they merge into a single, larger galaxy. This process can reshape the galaxies involved, triggering star formation, disrupting disks, and mixing stellar populations. It's a dramatic event on cosmic scales, though even a galaxy merger unfolds over hundreds of millions of years. Evidence suggests the Milky Way has absorbed smaller galaxies over time. The Milky Way hasn't grown in isolation, it has interacted with and consumed smaller galaxies. We see evidence of this in the form of stellar streams, long, thin ribbons of stars stretched across the sky. These streams are the remnants of smaller galaxies that ventured too close to the Milky Way and were torn apart by tidal forces. The stars from these smaller galaxies now orbit within the Milky Way's halo, though they retain a memory of their origin in their correlated positions and motions. Some star streams in the halo may be remnants of past mergers. The Sagittarius dwarf elliptical galaxy, for example, is currently in the process of being pulled apart by the Milky Way. Its stars are being stretched into streams that wrap around the galaxy. Over time, these stars will be fully assimilated, becoming part of the Milky Way's halo. This process has likely happened many times in the galaxy's history, each merger adding stars, gas, and mass to the Milky Way. Mergers are not always violent looking from afar. They can be slow, graceful reshaping. The word collision might evoke images of destruction, but galaxy mergers are not like car crashes. The distances between stars within a galaxy are so vast that even when two galaxies merge, direct collisions between stars are extremely rare. Instead, the galaxies pass through each other, their shapes distorted by gravity, their orbits altered, their structures gradually blending. From a distance, a galaxy merger might look like two clouds of stars flowing together, mixing and settling into a new form. The Milky Way is part of a group of galaxies called the Local Group. The Milky Way doesn't exist in isolation. It's part of a small cluster of galaxies, a collection of about 50 or so galaxies bound together by gravity. The Local Group spans several million light-years and is dominated by two large spiral galaxies, the Milky Way and Andromeda. The rest are mostly small dwarf galaxies, each with its own history and structure. The Local Group is our cosmic neighbourhood, the cluster of galaxies closest to home. One of our large neighbours is the Andromeda Galaxy. Andromeda, also known as M31, is the nearest large spiral galaxy to the Milky Way, about 2.5 million light-years away. It's bigger than the Milky Way, with more stars and a slightly larger disk. On a dark night, Andromeda is visible to the naked eye as a faint, fuzzy patch in the constellation of the same name. It's one of the most distant objects you can see without a telescope, and it's heading our way. Over very long timescales, the Milky Way and Andromeda are expected to interact. Observations of Andromeda's motion show that it's approaching the Milky Way. In fact, the two galaxies are on a collision course, but collision is a strong word for an event that won't happen for billions of years. Current estimates suggest that the Milky Way and Andromeda will begin to interact in about 4 billion years. They'll undergo a slow, complex dance, orbiting each other, pulling on each other, eventually merging into a single larger galaxy. This is a distant future event, not a near worry. By the time this merger happens, the Sun will be nearing the end of its life, expanding into a red giant. Earth, if it still exists, will be uninhabitable. The timescales involved are so vast that this merger is not something to fear, or even to think about in practical terms. It's just a reminder that the universe is dynamic, that galaxies evolve. that even structures as vast as the Milky Way are part of ongoing change. The universe is patient. Most of its stories move on deep timescales. This is worth repeating because it's so counter to human experience. We live in days and years. We see change on those scales. But the universe operates on timescales of millions, billions, even trillions of years. Stars are born and die over millions of years. Galaxies merge over billions. The universe itself is about 14 billion years old, and it will continue for untold eons. There's no rush, no urgency. Everything unfolds at its own pace, slow and steady, governed by the laws of physics and the patience of time. Just one more small fact, and then we drift. Light takes time to travel, even though it's extremely fast. Light moves at about 300,000 kilometers per second, the fastest speed in the universe. Nothing with mass can reach that speed, and even light, massless as it is, takes time to cross distances. From the Sun to Earth, light takes about 8 minutes. From the nearest star, over 4 years. From the far side of the Milky Way, 100,000 years. This delay is fundamental to how we perceive the universe. When you look at stars, you see them as they were, not as they are right now. This is one of the most poetic aspects of astronomy. The light that enters your eye tonight left its star long ago. Perhaps years, perhaps centuries, perhaps millennia. In a real sense, looking at the night sky is looking into the past. The stars you see are not as they are now, but as they were when their light began its journey, and there's no way around this. The speed of light is finite, and distance imposes delay. Some starlight began its journey long before you were born. If you look at a star 1,000 light years away, the light you see left that star 1,000 years ago. If you're seeing it tonight, it began its journey in the year 1026. Empires have risen and fallen in that time. Generations have come and gone, and all the while that light was travelling through space, carrying information about a star as it was a millennium ago. The Milky Way band, you imagine, is made of countless travel times layered together. Every star in that band is at a different distance, and so the light from each one has been travelling for a different amount of time. The combined glow is a patchwork of different eras, all arriving at your eye in the same instant. It's a mosaic of time, a visual history of the galaxy compressed into a single view. You're seeing the galaxy not as it is, but as it has been across a span of time. The atoms in your body were formed in older generations of stars. This is one of the most profound connections between you and the Milky Way. The hydrogen in your body dates back to the Big Bang, but most other elements, carbon, nitrogen, oxygen, phosphorus, calcium, iron, were forged in the cores of stars. Those stars lived, burned, and eventually died, some in quiet fade-outs, others in spectacular supernova explosions. In dying, they released their enriched material into space, where it mixed with gas clouds and eventually became part of new stars, new planets, and new life. Elements like carbon, oxygen, and iron were forged in stellar interiors. Stars are nuclear furnaces. In their cores, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. The process continues up the periodic table, building heavier and heavier elements until you reach iron. Iron is the end point. Fusing iron requires energy rather than releasing it, so fusion stops there. When a massive star explodes as a supernova, the explosion creates even heavier elements and scatters all that enriched material into space. Over time, that material becomes part of new stars, planets, and eventually living things. In that sense, your body is part of the Milky Way's ongoing recycling. The galaxy is a vast recycling system. Stars form, leave, die, and their material is reused. The atoms in your bones, your blood, your brain have been through this cycle, perhaps multiple times. They've been inside stars, blown out in stellar winds or supernova explosions, drifted through interstellar space, condensed into a molecular cloud, formed the sun and earth, and eventually became part of you. You're made of star stuff, as Carl Sagan famously said. You're the Milky Way, aware of itself. The galaxy turns quietly, whether you watch it or not. This is a comforting thought. The Milky Way doesn't need your attention. It existed long before you, and it will continue long after. Its rotation, its star formation, its slow evolution, all of these proceed independently. You can observe, you can learn, you can marvel, but the galaxy is indifferent. It simply is, doing what it does, following the laws of physics, existing on timescales that dwarf your life. Rest is also a kind of orbit, returning again and again to stillness. This is a gentle metaphor, a way to bring the cosmic back to the personal. Just as the Sun orbits the galactic center, returning to the same approximate region every 200 million years, you return to rest every night. You orbit through wakefulness and sleep, activity and stillness, and in that return there's a rhythm, a pattern, a sense of belonging to cycles larger than yourself. Tonight you don't have to chase any thought, because you're already held inside a slow, rotating home of stars. This is the final fact, and it's meant to release you. You don't have to hold on to any of this. You don't have to remember or understand or do anything. You're already part of the Milky Way. You're already moving through space, already connected to the galaxy by the atoms in your body and the motion of your planet. You're already home. And in that knowledge, you can let go, let your thoughts drift, and simply rest. Just one more small fact, and then we drift. Even in stillness, the universe moves, gently. This is the essence of it all. You lie still, but you're moving. Earth spins. Earth orbits the sun orbits the galaxy. The galaxy moves relative to others. Motion is everywhere, but it's quiet, smooth, not something you feel. It's a background hum, a slow dance that requires nothing from you. You can be still, and the universe will carry you. Let the Milky Way keep turning. It doesn't need your help. It doesn't need your consciousness or your awareness. It turns because it must, because gravity and momentum and the structure of space-time dictate that it does. And in that turning, there's a stability, a reliability. The galaxy has been turning for billions of years. It will continue. You can trust that, and let your thoughts drift with it. Imagine your thoughts as small, light things carried along by the gentle current of the galaxy's rotation. They don't need to go anywhere specific. They don't need to resolve into decisions or conclusions. They can just drift, like dust motes in a beam of light, like stars in a slow orbit. Let them go where they will, and don't hold on, until you don't need thoughts at all. This is the final invitation. There comes a point in rest where even thoughts are too much, where the mind quiets to near silence. That's where sleep begins, in that space where thoughts fade and awareness softens. You don't need to force it. Just allow it, the way you allow the galaxy to turn. Let your thoughts thin out, become less frequent, less insistent, until there's only the soft, quiet darkness and the sense of being held safe inside this vast, slow home of stars. Breathe in, breathe out. The Milky Way turns, you rest, and that is enough. The next story is about to begin. Please relax and enjoy.